Welcome, welcome. Thank you so much for coming. We really appreciate it. This is a Khronos Developer Day. So it's a workshop where you'll learn a bit about OpenXR, Vulkan, and also SYCL in the afternoon. We're starting off with OpenXR, and then we'll have like a lunch demo. After that is Vulkan and then SYCL. So yeah, let's get started. Okay, great. So a little bit about myself. My name is Alfredo Muñiz, and I am the chairman of OpenXR. I run a small startup called Exceed, and we develop full body motion capture system. We haven't launched our product yet, but we will soon. And it's going to be pretty awesome, and it'll be compatible. But I joined the working group, let's see, about a year and a half ago. And I noticed that it really needed a couple of changes, I felt. So I decided to, volunteer as chairman to try to put us on a better course. So people seem to like my ideas, and here we are. So a lot of the OpenXR members, they're more runtime, so, with the headsets. So it's very good that we have someone like me that's a little bit on the outside. That way we're not developing the standard for, just the runtime headsets. It's more open and there's more collaboration. It's worked well so far. I've received a lot of positive feedback. But we're constantly evolving, trying to involve more developers, and it's been a great journey so far. So hopefully it continues that way. Today I'll be talking, what is OpenXR for those that don't know. Maybe you're a beginner. How the group is organized, a little bit about how it works, what we've been working on, and then how you can help us. So to begin, and this is a very simple illustration. Our long-term goal is to do something like what happened with USB-C. Back in the day, if you remember, you had to connect to charge or to get data from a device. You would have all these different USB standards, USB-A, USB-B, mini, micro. And now the world's moving to USB-C. That's kind of how VR started. So we had all these different headsets. You had the Oculus, the Microsoft HoloLens, and they all required different code. So the developer would need to develop for that specific platform, which meant that if you wanted to make a game, you would have to maintain all these different libraries because all the headsets did something differently or they behaved a little different. And it was just a mess. And it is still currently kind of a mess, but it is a lot better than it was before. So hopefully that makes sense because that's the big idea. So, and it's not just on the, well, it is on the app developer side, but it's probably more than you think. So OpenXR isn't just about standardizing how developers talk to these headsets. It's much more than that. So there's also 3D displays. There's also fish tank designs. There's even the controllers. How do you get a controller to work with, the different headsets? How do you do body tracking, eye tracking, connecting these things to the cloud, Wi-Fi, 5G, even things like haptics, where the application developer, they don't want to care what the hardware is. All they care about is, does it feel the same way when I write this app? And that's really the big idea. So OpenXR abstracts away the hardware. We don't care what you're using. we want it to always work the same way. That way, when the app developer makes their game, it looks the same, it sounds the same, it feels the same, and you are completely immersed in that experience. So in the legalese terms, it's a royalty-free open standard, which means everyone has access to it. You don't need to pay for it. It provides high-performance access to augmented reality and virtual reality, which we call XR. And here's a nice little diagram that was made like 3 years ago that kind of illustrates the point. So again, before, you would have to maintain all these different libraries for each platform. And now you just go through the OpenXR API and they should all work the same. So why are we doing this? You know, who are we? What's this all about? So OpenXR is part of the Khronos group. So Khronos is a larger nonprofit organization based in the United States. And they develop open standards for a lot of different software and hardware platforms. You may be most familiar with Vulkan. That's our biggest group. But maybe you're more familiar with older things like OpenGL. That's been around for many, many, many years. So the way that it works is companies, they join the standards group. And when you join, you're able to contribute to the standard. So every group is run by a chair, and the chair kind of decides the direction of that group. In OpenXR, we meet every single week, and we go through issues and merge requests to develop new features, fix old bugs, revise the scope of the work. And the way we ensure that everything is consistent, because it's more than just code, you also need to actually test it on the hardware. So that's where the conformance comes in. So there's this whole group with a conformance test suite, and that ensures that when I run my code on a Meta or on a Microsoft device, it works the same way. So these products, they actually need to test against the OpenXR CTS and basically get approval, pass all those tests to be able to be called OpenXR compliant. And that's how we ensure that when the developer makes their one app, it actually works on everything. So it's more than just implementing it. You have to pass all these tests. So those are called adopters when you pass a test. And what I'm doing in OpenXR is I'm trying to get more developers involved too, because there are old ways that people do things, and OpenXR kind of shifts that paradigm, which I will explain a little later, to make it more future-proof and make it more XR focused. And a lot of that is educating developers. So a little bit of history. The group was founded in 2017, and we worked really quickly to develop a specification. So the initial one was actually released in July 2019. Of course, there was a lot of development after that. So we got a lot of support from game engines, such as Unreal in the back, even web browsers. However, because of the pandemic, things kind of slowed down. It was a little bit more, it was a little harder to meet and make regular progress. But so we had to kind of shift the way that we conduct our meetings, but I think we figured it out in the end. And now we're sitting in a pretty good spot. So recently, a lot of companies decided to completely discontinue their older APIs. So if you want to use, for example, the Oculus or the HoloLens, they no longer offer their legacy APIs. It's all through OpenXR now. And we're seeing that movement with a lot of these other companies too. And it's also being adopted worldwide. So companies like ByteDance and Tencent, they have joined OpenXR. So we do have support from the big players in the China region as well. So these are all of the members of the Khronos group. So some of these have exclusions for OpenXR, which means they don't really care about OpenXR. For example, Apple. Apple's a big company, but they don't do OpenXR. Maybe later, hopefully, but today they don't. But we do regularly have about, I think 60 people attend the weekly meetings, which is a pretty good number. And it's a broad representation. So there's about 30 companies from those 60 people. So I'm pretty happy with the representation in the industry, because it just means that when we come up with solutions, we'll actually do something that works for everyone instead of just something that works for one or two companies. So these are a couple of our adopters. I'm just going to show you the slide because I want to leave time for questions. One of the recent ones have been Magic Leap and Pico. And then Sony recently announced that their 3D spatial display, they're working towards conformance. So we're very excited to have Sony on board as well. In terms of engines, pretty much when you want to make a game in VR, it'll be supported by OpenXR, as well as WebXR. So as a backend, WebXR uses OpenXR, and it's nice because they only need to develop the one thing, and it should work on all of them. There's a lot of applications that use it. Some of the most popular, Minecraft, you've probably heard of it. And Blender, for example, has a plugin where you can go into VR and start using it in there, which is pretty nice. One of the most recent ones is KitWare's SPIR-V. So this is a scientific application. So it's not just video games. We're also looking at industrial applications that people use for OpenXR. I'll give a brief overview of how it works and what we're looking at. So again, we have the runtimes and we have the app developers. And in the middle is the loader. So the loader kind of tells the two where they are and how they speak to each other. And you can inject, you can intercept function calls using this method called API layers. So OpenXR was developed to be very flexible because we don't know what the future holds, but we want to make it open so that if something new comes out that we just did not think about, even though we speak for many hours, many days, many weeks developing these standards, there are still things that we just don't know will exist in the future. So that's where these API layers comes in. And that's where this concept called extensions comes in. So extensions can add functionality that we currently do not have. So for example, hand tracking. When companies were initially developing hand tracking, everyone had their own solution, right? And to get that to be together, we needed to spend a lot of time discussing, arguing, figuring out what is the way that works for us that enables all these applications without being restricted. And, you know, we're all kind of from an engineering background. So the way we think is very technical, which can lead to a lot of interesting conversations, a lot of interesting edge cases. And that's why it's a little difficult. That's why it takes time to actually go from just a vendor extension where it only works on one headset to an EXT where multiple people agree, and then finally a KHR where it's adopted by everyone. And the goal is to get everything from, you know, vendor, EXT, it's a KHR, and finally into the core. Because when it's in the core, that means everyone supports it. If you want to become OpenXR compliant, then you'll need to support it as well. And this is what I was saying with the API layers. So you can intercept different function calls, even from extensions, and modify them to use in your app. So it's a great tool for prototyping. And it's also a great tool for adding in additional hardware, such as haptics or body tracking. So I'm not going to explain this in detail, but I wanted to use the slide because one of the things that really gets app developers is that they want to know, what controller am I using? What headset am I using? But the OpenXR philosophy is to abstract that away. So it's we don't want a game to be built where they will change their functionality because it's a Quest and then do something else with the HoloLens. Like that is, we don't want that to happen because we think that's unsustainable. So instead we have this concept called interaction profiles. Instead of mapping physical hardware, we do interactions. So things like a click, things like poses or thumbsticks. That way it's more flexible. So you can have multiple interaction profiles per controller. For example, you want to use your controller as a, you know, normal joystick. You can also use that controller like as a gun or a knife. And each of those can change the button layout of the interaction. So that's the goal, and that's what we saw that was a little different from normal flat screen games where, you know, you have a controller, mouse, and keyboard, and that's very fixed. But in the virtual world, those things are actually, one controller can become multiple things because it's not the controller that matters, it's the experience, the immersion, what's inside. So we do have a lot of extensions, but most of them by Facebook and Microsoft. They are our biggest contributors, but everyone else has also contributed, and we kind of see it as kind of keeping them in check so that the biggest market player isn't the one with the loudest voice. So that's what joining OpenXR gives you, the ability to state your voice and bring in your opinion to shape the industry. And this is just some hand tracking. So we had to agree on where all these things are, the joint positions, the joint poses. And now when you pull up a game, most people support this. So it should be the same. So whether, it doesn't matter what hardware you use, you'll get the same hand tracking, which is very nice. And it took about a year and a half or so to finalize on that standard. And we're constantly improving it. So my priorities as chairman, first, developer first. I noticed that the previous chair, well, as engineers, we're kind of focused on what we're doing, but, you know, I think we should be focused on who we're doing it for and the actual problems we're trying to solve, and not get too pigeonholed on solutions. So I actually do bring in developers to talk about and give their feedback to us as a group. And it's been very helpful because we application developers and runtime developers are very different jobs, very different skill sets. So it's been very helpful to get that insight and then incorporate it into our workflow. Also want to optimize efficiency. So we have subgroups now. We're working on, we have a haptic subgroup, interaction system subgroup, 5G cloud subgroup. Basically, there's not enough time in the day to actually come up with that many solutions if we're only spending an hour every week. So there's more time now to break off, figure out a solution, and then implement it. And then, of course, documentation. We received a lot of complaints that people just don't understand OpenXR and they don't know how to get into it. It's very hard. So we have we're funding an OpenXR tutorials project, and that should be ready in a couple months. We're pretty excited about that. So here are some resources. I think these slides will be shared later, so you'll be able to click on them. But they're basically tutorials, things you can follow to learn more. We do have a Discord channel if you wanted more immediate feedback. And then we also have, I guess these are previous recordings of OpenXR where people like me or the spec editor have given presentations. One of the big ways you can help us, if you're a developer or if you just have feedback, we do review our GitHub, our public GitHub every week. So if you create an issue or ask a question there, you can also do it on the Discord, that's fine. But those are the avenues in which you can reach us. And then we do have, I do plan to start a monthly meeting for developer feedback. Before it was, you email me, we schedule a time, but it seems that people want it more regular. So I think once a month is probably good. And if you're interested in that, please let me know because we'd love your feedback.
As I said, I'm Jonathan Wright with Meta. I've been at Meta for 9 years since the Gear VR days and Rift days. So what is OpenXR? It's a standard for AR, MR, and VR, which provides developers with a way to access the capabilities of XR devices, which collectively we refer to AR, MR, VR as XR. So frame submission. Applications render eye views, one for the left eye, the right view based on the head pose. They submit that through an OpenXR API or APIs to a runtime, and the runtime is responsible for displaying that to the device display. When that happens, the runtime does a lot of things to keep the motion to photon latency, so the time between moving your head and the photons of the rendered scene hitting your eyes. We try to keep that really low. Modern systems are around 8 milliseconds or so. That technology is often referred to as time warp or asynchronous time warp or reprojection. And it basically can take images that were rendered in the past and kind of move them to the most recent head position. And it can do that in a variety of ways. Some ways are video encoding, motion encoding, decoding, just reprojection. But it's very important. This is one of the things that keeps people from getting sick. So applications generally aren't all that great at submitting frames every 60 seconds or 72 times a second, or once every 60 times per second, 72 times per second, 90 times per second, etc. Some headsets go much higher than that. But it's very difficult for something like a game to always do that. There are definitely games that do it, but the runtimes generally make up for this by presenting the last frame if a frame is not submitted in time for the current head pose. So another class of APIs that OpenXR deals with are tracking APIs. So some there are a lot of things that OpenXR tracks that you just don't have access to anywhere else, right? Like you don't have 3 DOF or 6 DOF positional controllers anywhere but in XR apps. So there's controller tracking, there's anchor tracking. Think of anchors as just places in a world, virtual or real world, that are trackable. There's scene tracking, so that might be like your desk or a plane on the wall. There's hand tracking, body tracking, face tracking, eye tracking. All these things are exposed through OpenXR. And then there's input. So input is related to tracking, and these controllers provide you input. But in this case, that's more like button input from controllers. And that's through what we call the OpenXR action system, which is worthy of a whole presentation or 3 all by itself. So won't go too much into that. So there's various other APIs. There's APIs for performance management. So to set CPU and GPU clock levels. These are important on mobile devices where high clock levels mean more power and less battery life. So if your application is doing something less intensive, like maybe in a menu, you might want to clock your GPU down. There's debugging APIs. Facebook provides color calibration APIs, for instance, so to help developers get a consistent, look across many different devices, as we ship a new device, every so often. There's rendering specific APIs. So foveation API is another one that Facebook provides. That allows the device to render with more detail right in front of your pupils than it does out to the side, because humans basically don't notice that. So that is a performance improvement that can be important. Some devices even allow for tracking eyes and changing foveation dynamically. There's haptics, which I think we all probably know what haptics is, but controller buzzing, force feedback, that sort of thing. Scene understanding, which I mentioned earlier, and then pass-through is another example of an API. Pass-through is allowing you to see kind of through your headset by seeing through a camera that's on the headset. And pass-through is really kind of where you get to the space in between VR and AR, which is MR, mixed reality. So what were things like before OpenXR? Alfredo went into a little bit of his history, so I'll try not to bore you guys too much, but there were a lot of different APIs for doing these things back in, say, 2015 or so. So we at Meta, which was Oculus/Facebook at the time, we had our own, 2 of our own, C API, VR API. Valve had OpenVR. Google came in with Daydream and Google VR. So everything was pretty fractured. If you wanted to develop as a developer, you had to choose the platform to develop for. And that's a hard choice to make. What do? You got to make your money back. You want to choose a platform that's going to pay you the most. And so that was actually keeping developers from getting into VR because there's not enough return on investment if you're stuck with one device. So as I said, that's fragmentation. It's bad for developers, especially in a new market, right? So you have a low number of users in that market, and you really need to reach as many people as possible. If you're stuck on one device, that's very difficult. Some other things that OpenXR does for us that make this, besides just unifying the APIs across developers and devices, it enables some innovation through vendor extensions. So we are able to have a standard API, but also provide new kind of subparts to that API that provide new functionality. And we do that in a standard way through the group. They're exposed to everybody in the group, and then other vendors are free to adopt those if we do it well. And through that method, basically, we're encouraging eventual promotion of these extensions across vendors. So we'll start with a vendor extension. It moves to something called an EXT, which is 2 or more vendors adopting the same extension. It may have changes in between there, but compromises. And eventually it can get up to what we call a KHR extension, and then even into the official spec over time as it's adopted by more. So, basically VR and AR have been a small pie historically compared to other things like, for instance, the Facebook platform, 1.7 billion users or whatever it is. So it doesn't make a lot of sense for us to be fighting over this at all from a platform perspective. So what we want to do is just make a much bigger pie for everybody. We want people to be able to write apps, or developers to be able to write apps that work on multiple platforms with fewer special cases. We have not eliminated all special cases. That's a dream we have, but we continue to work on that. That's a lot of hard work. We want you to be able to make money across multiple platforms. We really want developers, and this goes back to that question about what is the killer app, right? Like the more developers that are contributing, the more likely we're to have a killer app, the more likely we are to have multiple killer apps, or just a lot of different interesting apps that keep people engaged in AR and VR, and just grow the ecosystem in general. And so that itself will reach more users and just improves XR across the board. So then there's a question of like why we as Meta support this. Like we currently have the largest user base on VR devices, et cetera. So what are the advantages to us? Well, I just mentioned a lot of them, but I just want to bring forward this quote from Mark Zuckerberg in our founders letter in 2021. Privacy and safety need to be built into the metaverse from day one, but so do open standards and interoperability. So it's fundamental to what we're doing to proceed in this manner and to just improve the situation for everybody, because that's how we get into a better world. Now, from a little more my perspective, a little lower down the hierarchy than Mark Zuckerberg, OpenXR is important to us, not just for all these reasons, but also internally. We have multiple runtimes that are OpenXR now. So for us, this was an opportunity to take C API and VR API and make those one single API. That was a simplification for us. We were able to fix a lot of problems we created with our first APIs along the way. We've been involved in this basically since day one. Meta, my team submitted the first API proposal that was adopted as a starting point for OpenXR. It's changed significantly since then, but I just want to give some insight into why we are attached to making OpenXR a better place, a better API. And here's just an example of just some of the work we've put into VR and AR in the past. This is just a prototype wall from our Dallas office. These are mostly Gear VR prototypes. There's some Rift up there, but a lot of work goes into this stuff. And this is just a tiny fraction, of the research and input we've done to VR. So we're very vested in AR and VR. Yeah, so I think this might be a little bit of a duplicate, but just kind of to sum up, we have the two runtimes that are working on OpenXR right now. So our PC runtime, which supports Rift S and Link, that's an OpenXR runtime now. Our mobile Quest platform, that's also OpenXR. We even have a few internal implementations besides for testing, et cetera. So we'll be in this for a long time. Our devices continue to support OpenXR in the future because it's industry standards, cross-platform, cross-device, cooperative, and extensible. So I'm going to go real quick. I don't know what I'm at for time here. Yeah, so I'll try to go through this relatively quickly. I just want to walk through what an OpenXR application looks like, kind of at a high level, because it can be pretty daunting to get into. So hopefully this kind of will encapsulate it for people and just give you kind of a little bit of a starting point to understand what's happening. So OpenXR is a C99 API. That's for maximum API compatibility, just so it can be used anywhere, pretty much. OpenXR takes its cues from Vulkan API. So if you look at OpenXR. There's a lot of things that are going to be similar to Vulkan. That shouldn't be daunting. Hopefully it's actually encouraging for some people that are familiar with Vulkan, but it's not going to be as verbose as Vulkan, for instance. There's just not as many things to do, I would say. But the kind of the format of the APIs is very fun. So some basic concepts that'll help you in understanding this walkthrough. OpenXR has a concept of an instance, which is really, you can think of as global state or context for OpenXR for a process. So there's just one of those. There's only one allowed. If you try to allocate more than one, you can error back. And within those instances, there's a concept of a system and then a session. And a session you can think of as really more like the application lifecycle. So a session has a lifecycle, and that is driven by the lifecycles on OSs, whatever OS you happen to be running on. So for instance, on Quest, which is Android, that lifecycle is really driven by the Android lifecycle on start, on resume, on pause, stop, etc. So this is kind of the flow of an OpenXR application in general. There's some setup you do. And in fact, most of this setup, first two columns are set up, but you end up with a frame loop and some cleanup code. And I'll walk through those. So the first thing you do, you may have to do some platform specific initialization. For instance, on Android, you're going to have to pass the application context, which is an Android construct through a specific function for Android. Generally, what you do then is you enumerate extensions. So extensions are all the extra goodies that vendors have added. So if you're running on a Quest or running on a Vive or whatever, there might be specific things available to you that you want to utilize in that instance for that headset. So you enumerate what's available to you. Then you choose what you want to enable, and then you pass that to XR create instance to create the instance. After that, you really need to know what system you're running on. So one of the interesting things is you can be on a PC and you may have multiple headsets connected. So you might have a Vive connected, you might have a Rift S connected, or you might have a Quest connected, or any number of other headsets. So at this point, you also have to know what system you're on. You have to query the system, and then check system feature support for certain extensions. So the extension may have been advertised, but it may not actually be available depending on what the user selects as the current system. So if you have those three headsets connected, it's up to the user to choose which one is the current one, and that's the one that you see as the system when OpenXR instance is created. After that, you do your graphic subsystem initialization. So I think I missed saying this earlier, but OpenXR is basically graphics API agnostic, so you can use it with different APIs, Vulkan, DirectX 11, 12, OpenGL, OpenGLES. So once you've done all that, you're ready to create a session, and this is where you really start getting to the nitty-gritties here. Sessions, when you create a session, you need to enumerate your view configurations, because different headsets may have different configurations for their views. They may have canted displays. Technically you could have 3 eyes, and we would support that. I don't think any systems have done that yet. And then you basically start creating your spaces. So spaces you can think of as transforms. That when you want to get your the location and direction of your head, for instance, the pose, that's a space that you call XR locate space to get. And that will tell you, where the user's looking in your virtual world so that you could render the appropriate scene. Also, before actually starting the session, so you've created it at this point, you haven't begun it yet. This is where you create your action sets and actions. This is, like I said, a kind of a deep topic, but the idea of the action sets or the action system is it builds in some forward compatibility to input in OpenXR. So you can imagine you have a controller today that has AB on it, and you have a controller sometime in the future that has ABC on it. When you write your application, you create actions, so things you want to do in the application like jump, and you suggest to the runtime that jump should be button A, for instance, on the controller you know about at the time. Sometime in the future, there may not be that same controller with button A, but because the runtime knows what you suggest as a binding for a previously existing controller, the runtime can provide you with a real mapping back that is still useful. May not be ideal, but still useful. And this was important when making OpenXR because we knew that there was going to be a lot of innovation in the controller space. Like things just were not settled at the time OpenXR was being built. So yeah, so you do that. That's suggesting bindings. Then you attach action sets to that. Then you're allocating swap change. Swap change is what you render to. They're the images, essentially the buffers you render to that you then hand off to the runtime to have them displayed to the screen. The reason they're chains is because while the application's rendering to one, the runtimes need to be displaying that, right? So you're alternating, or you may be triple buffered, et cetera, when rendering these. All right, so then you get into the frame loop. The frame loop you start polling for OpenXR events. You will eventually get one that says the session should begun or the session is ready, and that's when you call begin session. And at this point, you're doing all your normal game logic. But what you want to do is you want to wait. You call XR wait frame because you want to know when you're ready to display to the screen, because it's very important in VR that you're displaying to the screen with every VSync, if possible. So wait frame waits for a VSync. It gives you a time to render, and then you call begin frame, do your application rendering, and end frame to submit your actual images once you've rendered it. In between all this, obviously, there's game logic, right? Or application logic. So your physics, you're running your physics, your networking, et cetera. There's no restriction. You can do all that on separate threads because wait frame is going to block for you until it's ready, it's time to render. And that's pretty much it. That's kind of what an OpenXR application looks like. Of course, there's the shutdown, you end session and destroy it, and then you destroy your instance. These are generally triggered by the application lifecycle on the device. So when you're starting to shut down, that's what you call these. All right, so that basically sums it up. I won't take too much longer. I just want to kind of real quickly go over some of the things we're thinking about, for the future of OpenXR. So we're identifying, reducing developer pain points. As Alfredo talked about, that's a big deal for us. And I hope my presentation kind of reflected that, because we want, it's important for the future of AR and VR to reduce these pain points. So the action system, as I mentioned, is complex. We know that. There are some things we're working on to improve it. System creation identification, that's a little weird right now because you may have to just call the system, get system in a loop until somebody plugs in their USB. Not really ideal. Color spaces, another thing we've been talking about recently, just because, as a developer, it's not great to make content for one device and then it's all, looks weird on a different device. Futures, event channels. So futures are just like futures you might be in standard library C, C++, similar to that. Event channels are a way for OpenXR events to be sent to different kind of subsystems or different libraries without worrying about one place consuming them all. Render models are a way for developers to actually get models that are the real model that the user has in his hand. So because that's going to differ per system, you don't want to have to hard code that into your app. You want to ask the runtime, what it is, and be able to display it. Spatial anchors, that's a generally an AR thing, but it's these locations in the real world that you can then reference and do things with, or place things at, etc. So lots of different extensions in the works. As Alfredo showed you, there's quite a few extensions we've been working on over the past few years from all sorts of different vendors. So, all right, well, that's it for my presentation. Hope that helped. A little bit of broad understanding of OpenXR. Obviously, there's a lot more detail that we could go into, but I'm happy to answer any questions if anyone has any.
All right. Hi, everyone. Welcome to How to Get Started with OpenXR in Unreal Engine 5. My name is Victor Broden, and I'm a product specialist at Epic Games, where my primary focus is on our XR development tools in Unreal Engine. There are several hyperlinks throughout the slide deck, which contains documentation, tutorials, and download links to useful software. You can find and download the slide deck from my Epic Dev community profile. I also believe you'll be able to find them in the shared folder from today's presentation. I know that we have discussed this a little bit in the past, but for those who are only watching this talk, in case they're only interested about Unreal Engine, I'm going to repeat it. So what is OpenXR? OpenXR is a royalty-free open standard that provides high-performance access to augmented reality, AR, and virtual reality, VR, collectively known as XR platforms and devices. It's an API for XR applications. It's the interface between an application and runtime, and a mechanism for interacting with VR, AR, and MR systems in a platform-agnostic way. The OpenXR specification should be used alongside engine documentation. It's the second link on this slide. And with that out of the way, let's get started setting up our development environment for Unreal Engine 5. First up, you either download and install the Epic Games Launcher, where you can find our binary versions of Unreal Engine. That is also where the Unreal Engine Marketplace exists, where you can find a plethora of assets to help you in your development journey. Or you can download the Unreal Engine source code from GitHub. It's also important to install Visual Studio 2022, as it contains prerequisites that are required to package a project containing the OpenXR plugin. Next up, you go ahead and download and install the runtimes for your XR devices. The runtime is the interface between your XR hardware and the application. If you switch head-mounted displays on the same machine that you're working on, you may have to switch which OpenXR runtime is the active OpenXR runtime. The active OpenXR runtime is set as an environment variable on your PC. You can change this manually, and while most runtimes provide this option in their user interface, I recommend a tool called OpenXR Explorer. It allows you to switch runtimes on the fly, but it contains many other useful features for OpenXR development. Source code, binaries, and instructions are available on GitHub, and I want to throw a big shout out to Nick Klingensmith for developing such a great tool. My days would look very different without it. Next up, for MetaQuest development, you need to configure Unreal Engine for Android development, and then install the MetaQuest A2B driver. And also make sure that you allow USB debugging on device. And I've actually seen a lot of people get caught up on this because you do have to put the headset on to allow that. That won't just work without it. So A2B won't respond without you allowing debugging on device, just like any Android device, really. And while on the topic of mobile XR, I wanted to share a couple of tips real quick. When you're iterating with MetaQuest, use Oculus Link because it'll allow you to just hit VR preview in the editor. And if the Quest is your primary platform, you can set the editor preview rendering level to Android Vulkan. So you get sort of a simulated rendering level of what it would look like on device. And then Screen Copy is a super useful software that will allow you to preview what's displayed on device. And it works when you're using Oculus via Link, as well as when you're running standalone on device. You can record, take screenshots, really helpful for development. And make sure that you use the device output log when running your application on device, as it gives you a real-time view into all the strings that are being printed out to the log. And I also want to mention that some vendors have their own developer tools. So if you're only developing for one or two headsets, make sure you check out their documentation for what other tools they have available. Now, support for OpenXR and Unreal Engine is enabled through the core OpenXR plugin. It contains an interface that can be used to develop plugins for OpenXR extensions. There are additional plugins you can enable for optional features, such as OpenXR Eye Tracker, OpenXR Hand Tracking. Some of these we ship with the editor, and others are developed and maintained by the vendors themselves. One of the native vendor extensions that we built a plugin off of and that we ship with Unreal Engine is the OpenXR Vibe Tracker plugin, which provides support for HTC's Vibe Trackers. It's available in Unreal Engine 5.2, and I wrote a little tutorial on how to use the new plugin on the Epic Dev community. Vendor extension plugins contain support for optional device and runtime specific features. As an example, if you download, install, and enable the MetaXR plugin, you'll have access to Meta's foveation and hand tracking extensions. Several vendor extension plugins are available on the Unreal Engine marketplace, but vendors can use other methods of distribution. Refer to the vendor's documentation on how to use their plugins. If you're interested in a deeper dive into our plugin architecture, my colleague and XR Engine programmer, Jules, who's here, will present a deep dive into the implementation of OpenXR in UV5 after my presentation. Now, a good place to start once your development environment is configured is the virtual reality template. It comes natively with the editor when you install it, and it's pre-configured for both PC and mobile HMDs. It contains examples on how to set up common features in interactions, such as teleportation, grab and interact with virtual items, a hand menu that works with either 1 or 2 controllers, very handy when you're developing and you're kind of holding the headset in your hand all the time, a spectator camera that allows you to view the scene and VR player from a free camera perspective, haptics, and spatialized audio. Now, next up, I'd like to go over some useful XR-related components and functions. The motion controller component binds to tracked input sources, such as motion controllers, hands, and vibe trackers. The motion source property defines which pose identifier the motion controller component should track. The pose identifiers that are available to you is the grip pose, which is, for example, used for interactions, such as grabbing a virtual item. The aim pose is good for teleport tracing or to do a line trace to interact with regular flat menus. And we also have the palm pose, which can be used for hand models, for example. Now, if the runtime doesn't support the palm pose extension, we fall back to the grip pose. That's good to know. The VR notifications component informs the application of system and user events, such as the play area being changed in the middle of the application's lifetime, or the head-mounted display being on and doffed. You just add it to a class, make sure that that's active in the level at runtime, and bind to the delegates that are relevant for your application. The XR device visualization component displays motion controller models when enabled. When display model source is set to default, the model will be selected based on the interaction profile chosen by the runtime. Custom models and materials are supported if you'd like to use the component, but with the option to override it, depending on which interaction profiles return, or for other reasons. And we're currently using a library of controller models that we ship with the OpenXR plugin, but this component will use the OpenXR render model extension in the future. Get play area bounds is a function that returns the length of the largest rectangle that can be found inside your play area. A common use case for this is to visualize the play area when teleporting, and you can find an example of this in the VR template. These are just a couple that I find useful, and for the lack of time today, I'm not going to go over them all, but you can head over to the XR development documentation to read about not all of them, but I think we have most of them up there. Now let's talk about input. Most interactive applications use motion controllers, and in our 5.1 release, we implemented OpenXR support for enhanced input. It's a recommended input system for OpenXR, and our legacy input system will be deprecated for OpenXR in the future. If you haven't made the switch yet, I recommend you read our documentation and tutorials on the subject. However, it's fairly easy to get started, so I'm going to dive into a little bit how to configure a new input mapping in the VR template for MetaQuest controllers. This is the Unreal editor. I'm running this in a 5.2, which I believe got released, or depending on what day it is in the US right now, it's being released today or tomorrow. And this is the VR template. This is what you see when you first launch the VR template. My monitors are switched, so this is a little interesting. There we go. Let's see if this works. All right. First up, we need to create an input action. An input action is an abstract game action that contains non-binding specific triggers and modifiers. To do this, We open up the content browser. I'm just going to change a view here so that we can see this as a list rather than big assets. We'll go to the input folder, actions, and here you can find all the ones that are already set up, but we're going to go ahead and create a new one. And this is actually not the view. I'll go back to task because I need a little bit of free space here. Right click, input action. We'll give it a proper prefix and we'll call it just OpenXR dev base example. There is nothing you have to do with this asset unless you would like to change the value type to be an axis 1D or axis 2D. These value types defines what kind of input this is. You can map them back and forth between them, but it's typically recommended that you use the value type that more closely matches the input. And so on a MetaQuest controller, the trigger, for example, is a linear it's a value from 0 to 1. And so we're going to go ahead and set this to be an axis 1D. Save that. Close it. Go back to the content browser. And if this works this time, great. Next, what we need to author is an input mapping context. The input mapping context contains suggested bindings for input actions and binding specific triggers and modifiers. An example of a binding specific modifier can be seen on the right, where I've added a custom dead zone modifier to the Oculus Touch grip axis for a better user experience when grabbing and throwing virtual items. Input mapping contexts are added and removed at runtime, and they are very powerful when designing context-aware input schemes. You can see an example of that in the VR template, where when you grab one of the pistols, we add a new input mapping context, and now your trigger is now being assigned to the weapon instead. It's important to know that you're only supposed to add bindings for hardware controllers that you use when you test your applications. Let the runtime pick the closest matching interaction profile for controllers that you don't own. This sets you up for future-proofing support for your application, so that controllers like the Quest 7 or whatever will work with your application, and you'll let the runtime deal with that. We'll go back to the editor. In the VR template, we already have the input mapping context, and so I'm just going to go ahead and open up the default one. We'll drop down mappings, and we'll go ahead and add our input action that we just created. And we'll go ahead and assign the Oculus Touch trigger, right trigger axis. So that's the controller I'm using. And we'll go ahead and save that. A little bit of window management is always good. This work. I have to manage the tabs and the all monitors here. The last asset we have to create to make this input work is a player mappable input config. And this is where we define the input mapping context and their priorities. You can have input mapping context, which is essentially what the equivalents of action sets are in the OpenXR specification. And they can override each other. We already have this in the VR template as well. So, and the input mapping context default is already added to it, but I'll go ahead and show it just for visibility. Here's all the context for the VR template, and IMC's default has a priority of 0. So when it gets added and there's no other input mapping context that's been added, it will take priority. We'll go ahead and open up the VR pawn, which is the representation of the player, and where most of the components that sort of transition between the real and the virtual world, like your motion controllers, live. If you haven't used Unreal Engine before, this might be the first time that you see what our visual scripting language blueprints look like. I pretty much build everything in blueprints, and many games do the same thing. It's essentially C++ and running in a virtual machine. And we can right click, we can find our input action, OpenXR dev base example, and we'll grab the event. You can also just return the value. And here, enhanced input is not complex, but there's definitely a couple of gotchas to it. And so if you're diving into this, I really do recommend you go ahead and read it, the documentation. Ben Hoffman, who's the primary engineer for this, made a really good tutorial, one on the topic itself and another on how to upgrade your project from our legacy input system to enhanced input. We'll drag off of started, and we're just going to print a string to make sure that our input works. And then up in the top bar here, we have our the option to preview our game, our scene. And if you don't see VR preview here, if it's grayed out, it means that you haven't set the appropriate active OpenXR runtime, the one that you're currently running, or you're not running Oculus Link, in particular when you're using the Meta headset. I believe similar streaming softwares for like Magic Leap, etc., HoloLens, they'll work the same. And so it's a typical gotcha, and make sure that's where using OpenXR Explorer is super useful. Just to always verify that you have the appropriate OpenXR runtime set. We'll go ahead and VR preview. There we go. I think the swap from battery to power was a little weird. And you can see that when I pull the trigger here, we could see that OpenXR is the best thing since sliced bread. It's just a quick little example on how you can add input, as it can be daunting, particularly folks who are moving from our legacy input system to enhanced input. The SteamVR OpenXR runtime has a rebinding UI that allows end users to customize mappings. Rebinding capabilities enables runtimes to add forwards compatibility, and it's important for accessibility, as it allows both developers and users to change the input mappings way after your application has been launched or even updated. And as the last note on input, you can enable support for OpenXR hand tracking with the OpenXR hand tracking plugin. It works with any device that supports OpenXR hand tracking. And note that both Meta and Ultraleap's plugins contains features for hand tracking specific to their devices. It's almost not allowed for an Unreal Engine XR developer to talk about XR without mentioning our rendering technologies, Nat and Lumen, since these are pretty much the biggest requested features that we get. But it's important to know that these are experimental. They only work on PC. And the deferred renderer, we have both forward render, which is what's default in the VR template, and a deferred renderer. And the deferred renderer running on DX12 is required for Nat and Lumen to function. And you should not expect good performance. This is an ongoing area of work for us, and we have no timeline on when we estimate performance to be good enough for support to leave the experimental state. But we have seen some really promising results, application running in like the 50-60 FPS range on a 4090. You can control that with a console variable called vr.pixel density, where you can lower the resolution and get fairly decent frame rates for some applications. I would not recommend it for games. If you are thinking of developing a game in the next year, you should probably refrain from using Nat and Lumen and revert back to using static lighting and the forward renderer. In 5.2, there are multiple improvements for XR development. These are a couple of them. I'm personally super excited about contrast adaptive shading. You can go ahead and read up on that. There are multiple similar technologies, but this is the one we decided to implement in Unreal Engine. And some of these technologies are, I believe they're going to be required for us to be able to run Nat and Lumen and very expensive rendering technologies on XR hardware at like 90 FPS. We also added the XR creative framework. This is really cool. If you're familiar with Unreal Engine, you might know that we've had something called the VR editor for quite some time. We have deprecated support for the VR editor and instead built an entire new framework that is built for OpenXR. VR editor was hard-coded to like the Oculus Rift and the HTC Vive, and it pretty much only worked for them, and it was a nightmare to maintain. So now we have this framework that will allow not only us, but any developers to develop in-editor VR tools. Some examples of that could be in-editor modeling, animation. It's primarily used by virtual production and for directors of photography to scout scenes before they put them on like one of the big LED stages, or for any other form of virtual production. We did see a 5% GPU performance improvement on Quest 2 with some of the shader optimizations that we've done. This is our ongoing work to unify our rendering pipeline for n views rather than if left, if 0, if 1. And since I do have a little bit of time, I just wanted to mention a couple of tips and tricks. You can lower the preview window resolution of your application. The preview window is what you see up here when I hit VR preview. That is not the same image that I'm seeing in the headset. And that actually costs the GPU a little bit to render. And so whether you do that when you're iterating, in case you're on a not such a high-end machine, or when you ship your application, you can lower that. The user can still enlarge it if they want to do, screen capture or do a Twitch stream or something like that. But by default, that will just make your application run a little better. Printing strings in VR, as you could see, it's like in the top left corner. That can be difficult in some headsets to see. And actually, since I do have time, I'm just going to go ahead and do this live in the editor. What I like to do, if we open up the VR pawn again, I like to make a little macro. So if we grab a print string function right here, I know this is hacky, but it's super useful, so I want to show it. We append to that, and here we basically just add a bunch of line breaks and then a couple of spaces to your taste. And then whichever, go ahead and make some room. Add a literal string node. We can drag out this execution node, add a reroute, and this is just a handy way. We can do the same thing here. This is just a handy way to mark this, right click, and we can collapse it to a macro. And now we'll name this VR print string. And so if we go ahead and use this instead of the print string that I did earlier, we'll compile, save that. And we'll pi that again. Not the OpenXR pi, but it stands for play and editor. We just call it pi. And now when I'm pulling that, you should see it a little bit further to the right and in the center. And in the HMD, it's a lot easier to read. And for the last tip, particularly if you're developing a multiplayer game, when you are testing that in editor, you can't have, so far yet, you can't have two HMDs plugged in. And even then, I don't really know how you're supposed to use two of them at the same time. It's really useful to build a mouse and keyboard debug pawn so that you can play an editor without VR and test your application in a simulated networked environment and just tab between your different windows of the different players. It's crucial and a lot better than sitting with 3 computers and uploading builds to every single one and moving headsets around. It will save you some time. It works for single player games as well, but for multiplayer, that's really where it shines. Thank you. That's all for me. If you have any questions, I'm more than happy to answer them, and I'll be around for a little bit after the OpenXR presentations here are done as well.
Hi. So in the talk before mine, Victor showed you how to use the OpenXR plugin. In my talk, we will dive deeper into more the actual implementation of OpenXR within the Unreal Engine. You do not need to know any of this to work on your game project, but it might be useful if you want to debug the inner workings of OpenXR within Unreal Engine, or if you want to extend it for your own purposes. So my name is Jules Blok. I'm an XR programmer at Epic Games, and I've been with the OpenXR working group for about 6 years, both as an individual contributor and as a representative for various companies. So the first thing I'd like to look at is the implementation of enhanced input in the engine. So enhanced input was developed independently from OpenXR. It was primarily developed for the purposes of Fortnite. But it happened to be that it matches very well to the concepts within OpenXR, which also kind of confirms to us that the design in OpenXR aligns well with what games actually need. So this input system was introduced in UE5. The support was added in 5.1 and improved further upon in 5.2. As Victor has mentioned, it is the default input system within our VR template. So as Victor has shown, two of the main assets within enhanced input are the input mapping context and the input actions. So within OpenXR, the input actions map very well to just the XR actions within the OpenXR spec, while our input mapping contexts are more of a collection of the action set and all the suggested bindings for the actions within that action set. So as I said, the actions map very directly. We simply have an asset name for the action that is used as the action name within the OpenXR system. There is also a localized name that you can give in your asset, which is the action description. We give that a localized name to the OpenXR action system, which is then displayed by the runtime if it has a user rebinding UI. All the value types within OpenXR are supported. However, haptic actions and pose actions are handled outside of enhanced input. We also support modifiers and triggers on actions, which you can see in the bottom right. We have a dead zone on this action. And these are handled by enhanced input itself and are not exposed to OpenXR. It's just a filter that's being executed on the action data by the engine itself. So the action state can be retrieved by a project using blueprints. So we have a more event-based system where we simply communicate to the application that an action has been triggered, it has started, whether it's ongoing, whether it's been cancelled, or whether it's completed. The action value can then, after an event is fired, the action value can be retrieved from the action value pin. It can be retrieved as either a float or a 2D vector. Enhanced input also supports 3D vectors, but since there are no 3D actions in OpenXR yet, these are treated as 2D vectors for the purpose of OpenXR. So, as I said before, the input mapping context is a collection of both the bindings for the actions in the action set and the action set itself. So the action set name is based on the asset name for your mapping context. And within the asset itself, you provide a binding to the inputs on the controllers for each of your actions. So these are then used to generate the XR action suggested bindings, which are then given to the OpenXR runtime at the start of the application. We also use the input mapping context to detect which interaction profiles you're using within your project. So for example, we can see here that we're using the Valve Index interaction profile, the Oculus Touch interaction profile, the Vive interaction profile, and the Mixed Reality interaction profile. So OpenXR operates with input paths internally, while the Unreal Engine works with key names. So we've created a mapping between the key names and the OpenXR input paths. We basically tokenize our key names and then map them to various parts of the input path. So for the start, we use a Vive to map it to our Vive interaction profile. And then we tokenize the right for the user hand right, and trackpad and Y for the components, input trackpad and the Y axis on that trackpad. We also support the binding modifiers, as I explained before. We also support those in the input mapping context. So you can use binding modifiers to provide modifications to inputs based on the actual controller that's being used. So in this case, we've provided a dead zone that's specific to the Oculus Touch. So if you have differences between controllers, like trigger on an Oculus Touch may behave differently from a trigger on a Vive controller, this is the way where you would set different dead zones for the different controllers. We do not yet expose these to the OpenXR runtime, but we will do so in the future. So these may be adjustable by the user in some cases. So we don't recommend that you use these for gameplay logic. We recommend that the gameplay logic is done through action modifiers, while controller-specific bindings that may be modifiers that may be changed by the user are done within the input mapping context. We also have the ability to define completely custom modifiers within a blueprint class. So here you can see on the left, we get the input data as an input, which we can process using nodes in the blueprint and then provide an output on the right that would be the final value of this action. So to activate an input mapping context and make your action set active within OpenXR runtime, we have the add mapping context blueprint node. This basically maps to the XR active action set within OpenXR, which is provided at the point where we call XR sync actions, which is where the OpenXR runtime processes its input. We also can provide a priority number here at runtime. However, we currently have to provide that through an extension, as the spec defines that priority numbers are immutable from creation of the action set. So to allow for this at runtime changing of the priority numbers, we do require support for an XT extension. This extension is supported across most runtimes right now, and we hope to have support across all runtimes soon. There's one last asset to talk about, which Victor also mentioned earlier, is the player map input config. It is currently used to get an enumeration of all the input mapping contexts during your project that are used for OpenXR, and to provide default priority numbers for them that are used at action set creation. Currently, it is required that you provide a profile such as this to make use of the OpenXR action system. But in the future, we will enumerate the input mapping contexts in your project automatically, and you will no longer need to provide this asset. So in Victor's talk, he briefly mentioned interaction profiles. I'd like to go a bit deeper on that. The interaction profiles within OpenXR are basically collections of input paths for a specific controller. So for example, here we have the Vive controller, the mixed reality controller, the Oculus Touch controller, and the Valve Index controller. So by using a key from any of these profiles, you signal to the runtime that your project supports this controller. From the profiles that your project support, the runtime will select the profile that is closest to the physical controller the user is actually using. So, for example, your project could provide just bindings for Oculus Touch and for the HTC Vive controller. So if somebody is using a Valve Index controller, the runtime may choose that it matches most closely to the Oculus Touch controller and will only activate the bindings from the Oculus Touch profile. So you have to be very careful here that you don't have any lingering bindings to any of the other profiles that you don't intend to fully support. So make sure you don't, for example, accidentally provide an extra binding to just the menu button on the mixed reality controller, because if that controller is the closest thing to the physical controller the user is using, you will only receive input on that binding. And it would prevent the runtime from selecting an interaction profile that is more appropriate that you fully support. So while we try and make sure that you never need to know the interaction profile that's actually being used, it may sometimes be useful to know which profile the runtime has selected. So you can do this by calling the get current interaction profile blueprint node. But since a runtime may change the interaction profile at any point, and it may not be immediately available, we do recommend you query it based on an event, which is the interaction profile changed event. Also, we recommend that you try and use binding modifiers first to solve issues such as this, to avoid having big switch cases within your project where you switch on based on which interaction profile is being used. There are some limitations right now with the binding modifiers and within the actions. So there is an extension in OpenXR, it's KSR binding modifications, which is not yet supported by enhanced input. We currently handle all binding modifiers within the engine itself. This does have a small problem, is because the physical inputs are abstracted away from us, and we do not always know exactly which binding was activated. So we have heuristics based on which hand the action is triggered on and which interaction profile is being used. We use that information to try and select the binding modifier that's appropriate. But there may be a case where if you have multiple binding modifiers on the same controller for the same hand, where we may only select the first one and ignore the second one. So try and use binding modifiers sparingly on the same controller. There's also within the input action itself, there's the ability to turn off consume input. Consume input basically means that a higher priority action will consume the input and not allow a lower priority action to receive the same input values. This is currently the default behavior in OpenXR with no way to switch that off. So if you try and turn off this flag in your action, it will currently be ignored by the engine. So avoid turning off the consume input flag in your projects for now. All right, that's everything on enhanced input. I'd like to talk now a bit about an API we provide in our engine to allow you to extend our OpenXR plugin and provide their own support for OpenXR extensions or other features you may find useful. So the OpenXR extension plugin consists of an initialization interface, which allows you to communicate to the engine any extra extensions you may want enabled. You can provide both required extensions that are required for your plugin to be considered active, and some optional extensions which won't affect whether your plugin becomes disabled or not. As part of the extension plugin, you can receive callbacks. They're kind of similar to how API layers work in OpenXR, where we will call a callback based on an OpenXR function, it will be called. And you can then provide extra extension structures that will be inserted into that OpenXR call. So let's take a closer look, for example, at the uncreate instance callback. So the function signature for uncreate instance provides you with an interface to our OpenXR HMD plugin, which allows you to fetch things from our engine like the XR instance and the XR system. We also provide the current head of the next chain, which is where you can provide extension structures to a function call. And we allow you to return a new head to the next chain. So when you want to insert an extension structure into the next chain for this function call, you basically assign the next pointer that you give as an input to the next pointer of your extension structure. then you make sure you keep this extension structure in memory and return a pointer to that extension structure to be the new head of the next chain. It's important that you don't let this structure go out of scope because we need it to stay alive until the next call to this callback. So you can either, make it a member of your plugin or mark it as static. So let's look at how to use the extension plugin interface to add a new controller to the engine. So first, you need to make the engine aware of the input paths and input keys for your interaction profile. So to do that, you use the add key function within our eKeys interface. So this allows, when you add keys for your interaction profile, you allow the project to know which keys your interaction profile supports and allow us to generate input paths for them. You need to call this API even if your interaction profile extension is unavailable, because if you don't and people run their project on a different runtime, they'll get a bunch of warnings about missing keys. So try and always provide the keys for your interaction profile. Since the engine doesn't deal with interaction profiles directly, you need to provide a mapping from your interaction profile from a key prefix to your interaction profile path, which you do through the get interaction profile callback. This maps the prefix to your interaction profile path and also signals to the plugin that it needs to add pose actions and haptics actions to your for your interaction profile. The haptics outputs are optional because some controllers may not support haptics. So you can indicate in the output parameter as haptics whether your controller supports that. So let's look again at the mapping between a key identifier and an input path. So in this case, this is for the HP mixed reality controller extension. So we provide a prefix called HP mixed reality controller and then map that to the interaction profile HP mixed reality path. And we then also add the left trigger axis to identify one of the input paths supported in the interaction profile. And we then do this for all the input paths in the interaction profile to make sure they're all known to the engine and can be used within projects. For consistency with the rest of the engine, we have made a small change, is that we use the word axis to mean value, because this is consistent with how we've always called analog values within our engine code. So just to reiterate on the function calls, so for the HP mixed reality controller with the get interaction profile callback, we would provide a key prefix HP mixed reality controller, and the output path for this prefix is the interaction profile path. And then for add key, we provide the HP mixed reality controller left trigger axis key. And you would do this then for every key in your interaction profile. We also have the ability to add custom motion sources. So motion sources are the tracked poses within the engine. And by default, for controllers, we will add a grip pose and an aim pose. But there may be cases where you have to provide completely different poses. So one example here is our support for 5 trackers. 5 trackers are completely different from the way that usual controllers are handled, because you would use that to track parts of your body. So you don't need just poses for grip, you need poses for your chest, your arms, your legs. And we do that using the iMotion controller interface. So iMotion controller has a call to enumerate all the sources within your extension. And these will then be exposed as motion sources to the project. Then when we want to actually retrieve a pose for this motion source, the engine will call get controller orientation and position, which will be passed in the name of the motion source and you can then provide an orientation and a position for that pose. You will also need an ability to make sure that your action, your pose actions are synced with the rest of the actions within the project. To do that, you add your pose actions to an action set, which you can then provide to the engine in attach action sets and get active action sets for sync. This allows you to actually sync the pose data for your custom motion sources, so that you actually get input from the OpenXR runtime when you try and locate the poses. So now that I've talked about input, I'd like to talk a bit more about how we integrate our rendering pipeline within OpenXR. So UE5 is a render pipeline that is multi-threaded and can operate on multiple frames simultaneously. The most important threads we deal with are the game thread for simulation, the render thread to set up our rendering, and a submission thread to actually send the work to the GPU's queue. To integrate this with OpenXR, we need to very carefully manage the swap chain state, as multiple swap chain images may be acquired at the same time. The render thread needs to know what the next swap chain image is going to be that we're going to render into, which ideally means that we would call XR acquire swap chain image on the render thread. However, the OpenXR specification currently requires that XR acquired swap chain image has access to the GPU's queue in the case of the Vulkan extension, which means we cannot currently call XR acquire swap chain image on the render thread, and we need to find an alternative solution. To show that alternative solution, let's look at a few frames going through our render pipeline. So here you can see the different threads within the engine, and I've also added one more line for the GPU. So on the game thread, we will first start simulating a frame. So we'll do our gameplay logic, our physics simulation, and then we will call XR wait frame to suspend the game thread for the next frame. We will then, after XR wait frame returns, simulate the next frame and continue doing this for the next frame after that. So once we're done simulating a frame of the game thread, we want to start rendering this on the render thread. Before we can start rendering, we need to acquire swap chain image to do that. And currently, that means the render thread has to be suspended to wait on the submit thread to have time to acquire an image. So it will then wait on the submit thread to call acquire, and then after that has succeeded, it can return to the render thread to do the actual building of command lists that will be sent to the GPU later. This then also happens for subsequent frames. So on the submit thread, after it has been acquired and the first few command lists have been built, we can start submitting them. Before we can submit any work, we have to call wait on the swap chain image to make sure that the compositor is done rendering to that swap chain image and we can actually render a new frame into it. After wait returns, we can call submit to actually start some of this work on the GPU. And once we've submitted all our work, we can release our swap chain image. And after that, we can call XR end frame, which is indicated by the diamond at the top there and a line that goes vertically down. As you can see, GPU work may actually extend beyond XR end frame, and there is fencing to ensure that the image won't be displayed until it is actually done rendering on the GPU. This also then happens for future frames, and now we have a complete picture of how frames travel through our render pipeline. One thing we now want to solve is we would like to move build command lists further to the left so that we can do more work ahead of time. So one way we do this is by shifting when we acquire a swap chain image. So instead of acquiring the swap chain image for the frame we're currently trying to render, we're going to acquire the image for the future frame. So in this case, we can already assume the image is acquired when we're rendering the white frame. And we acquire an image for the yellow frame so that we have one ready ahead of time for the render thread to build command lists for. So this way we can move our bubble for build command list further to the left and do more work ahead of time, leaving us with more room on the render thread to have the frame go long if necessary. However, this will break down if there are ever more than 2 frames going down the pipeline at the same time. So to allow for any number of frames up to the maximum that the swapchain supports, we would like to move the actual acquire to the render thread and have only the wait and release happen on the submit thread. So this way, whenever the render thread wants to build command list for a frame, we directly acquire a swapchain image on that thread. However, this will require changes to the Vulkan extension to allow us to acquire swapchain images without having access to the GPU's queue, which only the submit thread has right now. Hi, that was my talk. Thank you very much. If there are any questions, I'll be happy to answer them.
All right, thank you all for coming today. Hopefully it's been an interesting morning for you. So my name is Neil Trevett. My day job is at NVIDIA. I'm also serving as president of the Khronos group. So I have a bridging presentation between OpenXR this morning and Vulkan this afternoon. I'm going to spend just a few minutes just talking about Khronos as an organization, how we're organized, some of the key projects and standards that we have underway, and hopefully encourage everyone to get involved. So let's dive in. So if you obviously you've been listening to the OpenXR folks this morning, but if you haven't come across Khronos as an organization, we are a non-profit organization. We're a standards organization that is committed to create open, royalty-free standards. We like to say connecting software to silicon, low-level APIs so that applications and libraries and frameworks can reach down into hardware acceleration in domains like 3D graphics, XR hardware that you've been hearing about this morning, general parallel compute, including inferencing, vision processing, and we make all of these standards freely available to the industry. We are member driven. We have around 200 members and they're global. Around 30% of our membership is based here in Asia. But before I dive into Khronos as an organization, just perhaps answer the most basic question is why open standards? In fact, what is an open standard? So Khronos, we're typically talking about interoperability standards, and an interoperability standard is a specification that enables 2 things to communicate. It might be hardware and software, like most Khronos APIs. It may be a client and server device. It may even be 2 organizations. But technical interoperability standards like Khronos APIs are really the way that we can enable technology to be pervasively available. A well-designed interoperability standard is a specification like OpenXR, together with performance tests, so we can genuinely enable multiple implementations underneath an API standard, so we can have pervasive availability of functionality like OpenXR available for multiple vendors across the industry, while each of those vendors is able to innovate in their own implementation. And this is very different, very complementary to open source, which is the exact opposite, where multiple companies are focusing on a single implementation, specifications are enabling multiple implementations. So a technology can be implemented by multiple companies and be available across the industry. A well-designed open standard has a very clear view on what it's trying to achieve in the market. A well-designed open standard can grow the market by reducing customer confusion and increasing the capabilities and the usability of products. It can reduce costs in developing new standards because you don't have to design everything yourself. You can pick up a well-formed open standard. You can speed your time to market because there's less work to do, leveraging open standards. And a well-designed open standard actually enables innovation. It doesn't dumb down implementations. It enables everyone who's implementing a standard to really innovate in how they deliver that standard functionality. And again, well-timed open standards. We don't do R&D by standardization committee. Standards should be formed when the industry wants to have an open standard. They want to have a standard way to access functionality, and differences in proprietary solutions have become a barrier to business. That's the correct time to create open standards. And the most effective open standards, we believe, are created under multi-company governance, where there's no one company that has control. It's a very democratic, consensual process to create standards under a well-defined intellectual property framework, so they can be used royalty-free in the industry. They can be extended by vendors who want to innovate out ahead of the standard, and a thoughtful level of abstraction. So you provide portability by being high enough, but you also enable innovation under the API standard. You don't want to stifle innovation by being too low. So Khronos is an organization. We have a number of guiding principles. We're open to any company that wants to join. We do have a strong IP and intellectual property rights framework to guarantee that our specifications will not be subject to royalties from the Khronos membership. We try to figure out how we can invest our time and effort in standards that are going to create a real difference in the industry. Any member at Khronos is free to propose a new standards initiative at any time. We have a lot of investment in conformance tests and adopters programs. So we try our best to make sure that conformant implementations of Khronos standards are reliable and effectively deliver that standard functionality. And we are a non-profit. Although there are membership dues, which pays for the work that we do, all of the revenue that we receive gets plowed back into our mission to deliver these open standards to the benefit of the wider industry. The way we organize internally, you've seen OpenXR this morning, you're going to see Vulkan this afternoon. Each of these standards, and there are many others in Khronos, we'll get to that, but each of these standards are driven by its own working group. So the members within Khronos can choose to join any of the working groups that are relevant to their business and participate in the working group process to create and evolve and maintain these standards. Each working group will have a whole series of deliverables, the specification itself, the conformance test suite and adopters program, so people can test and prove that they are conformant, documentation, samples, educational materials, and all those materials are typically made freely available out into the industry. So here is the roster of currently active Khronos standards. And I'm going to just, over the next few minutes, highlight some of the most active ones. I won't go into too much detail, but you can see that the groups, the standards we have at Khronos are grouped into domains. We have a number of 3D graphics standards. The OpenGL was the granddaddy of all 3D open standards, the new generation Vulkan API, WebGL, bringing 3D to the web, the new Inari, which I'll talk about in a moment. So I think probably 3D is certainly where we started at Khronos. Is probably still the majority of our efforts around the 3D space. In addition to the 3D APIs, we have 3D asset formats. GLTF is the one that's most widely used in the industry. It's a asset format to efficiently transmit 3D assets around. It's a very good complement to Vulkan and OpenGL and WebGL. We have OpenXR, which you've heard about this morning for portable XR, and a whole family of APIs for parallel computation and vision processing, inferencing. And one of our newest working groups is the Khronos group, which is a camera API, which I'll give just a little more information on in just a moment. And then last but not least, down at the bottom, often we find the industry demand to take the commercial kind of desktop or mobile APIs and create safety critical versions of those APIs. We've done that in the past with OpenGL and Vulkan. So we have OpenGL SC and Vulkan SC, and now we're working on SYCL SC. So let me just spend a couple minutes picking out some of these standards. Vulkan, if you can stay for this afternoon's session, you'll get a lot more information on Vulkan. But the high order headline on Vulkan, it's a GPU API. We like to call OpenGL was a 3D graphics API. Vulkan really at its core is more of a GPU API. You're using the hardware in a GPU much more explicitly, both for compute and graphics, of course. OpenGL was a higher level API, a lot of machinery in the driver itself. Vulkan, the driver is much thinner. So the application has more explicit control over the hardware, which means the application also has more responsibility to do more of the work that the OpenGL driver used to do. But the demand from the developer community was to enable this lower level, more explicit control over the hardware, because the application often knows better than any driver what they want to do. So Vulkan is designed to enable developers to get the very maximum performance out of a GPU for both graphics and compute. And in terms of the ecosystem, it is kind of interesting. Vulkan is the only GPU API in the market that is not under the control of a single company or a single platform. DirectX and Metal are both excellent APIs, but they're owned by Microsoft and Apple. If you want portability across multiple platforms, and you think the industry is well served by having a GPU API that's controlled under multi-company governance, then Vulkan is the only choice in the industry. Inari hasn't shipped yet. It's getting close, and Inari stands for Analytic Rendering Interface. Its beachhead application area is scientific visualization. It's a much higher level 3D API than Vulkan. Vulkan gives you explicit control of the GPU hardware. Inari is much higher in that it just gives you the ability to describe a scene. And that's the first time that we've had that level of high-level API to present us a scene to different renderers in a cross-vendor portable way. And then the renderers will take that scene description and render a scene without the programmer having to provide any of that rendering low-level information. Scientific visualization is the beachhead here. There are a number of scientific visualization packages that just want to drive different types of renderers. They're generating scene data. Their main mission is not to be a rendering engine. They just want to hand off to a rendering engine. And Inari is going to enable that to happen in a very effective and portable way. And although we started with scientific visualization as the first domain, I think Inari is going to find wide usage across many different domains for people who just want to do the rendering without getting involved in the details. We already have multiple sample implementations, and we're planning to finalize the specification in the third quarter of this year. Our 3D asset format that goes alongside these 3D APIs is GLTF. It's a 3D asset format that's been designed for a very efficient runtime deployment of 3D assets into the web, into high-end devices, into low-end devices, really anywhere where you need 3D. GLTF can deliver it to you. In fact, this is standard PowerPoint, and GLTF is supported by Microsoft in PowerPoint. So that's not a video, that's a GLTF model being animated by PowerPoint. GLTF is very widely adopted in the industry. It's now an ISO standard, which gives it extra stability, and we have a very active roadmap. PBR, physically based rendered materials, is one of the areas that GLTF has been concentrating on over the last few years. We've had multiple ways of increasing PBR functionality. There's some examples here: translucency and transparency, sheen, and there's an ongoing roadmap to produce even more sophisticated PBR. We're bringing audio into GLTF, behaviors. So an asset can encode an interaction behavior. So if you have an alarm clock that goes off, you can press the top and it will stop, for example. You can encode all of that into a GLTF file very soon. We're going to have simple scene composition where you can bring multiple GLTF assets into a scene. We're bringing physics into GLTF, some extensions to cope with the very large data sets that we have in geospatial applications. GLTF is widely used in geospatial right now, but we're going to have additional compression options, and we're going to be enhancing the animation functionality in GLTF files. So a lot of work going on in the GLTF working group. The family of compute APIs also has a lot of work and investment going in by multiple working groups. Moore's law is arguably dead, and so we're not getting more compute by going faster and faster with smaller silicon. We need to go faster by having parallel processing. And this family of Khronos APIs are different styles of API for different use cases, but they all boil down to how can you harness parallel processing to accelerate applications. So at the bottom layer here are the low-level APIs close to the hardware, pretty explicit control over hardware. We've talked about Vulkan already. Vulkan has compute queues as well as graphics rendering queues. You can use HLSL shaders or GLSL shaders in Vulkan to do compute. We have OpenCL, which is a full-on compute API where you're not tied to GPUs. Vulkan is a GPU API. OpenCL is a more generic programming model where you write small kernels in OpenCL C or C++, and then OpenCL gives you all the machinery you need to compile those kernels and distribute the work out across any available processors, be they multiple CPUs, GPUs, FPGAs, DSPs, custom hardware. But you're still working quite close to the hardware. At the top row are higher level abstraction programming frameworks. SYCL is using standard C++ syntax to enable programmers to indicate which parts of their C++ application in a single file gets distributed out onto parallel hardware and runs on the host. OpenVX is a graph-based API, so you can construct a graph of vision and processing and inferencing operators that connect together in a graph and will be executed at runtime. And because you're describing a graph, You don't have to describe anything about the hardware, so it's very portable across different hardware architectures. And last but not least, we have two file formats. So SPIR-V on the bottom layer is an intermediate representation, which is a common compiler target. So if you compile shaders or compute shaders, you can compile those and feed those into the Khronos APIs. And lastly, we have NNEF, which is a neural network exchange format. And APIs like OpenVX like to take in a graph description because it lets the implementer do a lot of graph level optimizations for inferencing operations. A lot of these APIs, both on the graphics and compute, are increasingly being used outside desktop and mobile, being used in embedded systems. And many of those embedded markets are increasingly needing safety certification, autonomous vehicles, drones, robots, safety certification using the relevant ISO standards, for example, are becoming more and more demanded in deployed systems. And for anyone who knows about safety certification, you have to test everything and document how you're going to test everything and then test the documentation. It's a lot of work. And if you have a line of code that's not needed, that's a lot of work to test and document that line of code that is not necessary. And so the safety critical APIs take the commercial version and then try to take out everything that it wouldn't be needed in a safety critical system. Now, games using Vulkan on the desktop love to have a lot of dynamic functionality. You don't typically need that in embedded systems. So Vulkan safety critical would remove that functionality so you're not adding to the certification load, and increasing reliability through having static memory allocation, better error reporting, anything we can do to help testing and reliable operation for functional safety certification. So it turns out we've been doing this safety critical subsetting for quite a while. We started with OpenGL SC, which is a subset of OpenGL ES. Vulkan SC is much newer, shipped in 2022. OpenVX, that's the graph-based programming model, has a safety critical profile that shipped in 2019. And our newest working group is SYCL SC, which is taking the C++ based SYCL programming framework and creating a safety critical version of that. Another very common element in embedded systems is cameras, because a lot of embedded systems, like autonomous cars, for example, they need, of course, to be constantly understanding their environment. More sensors being used in these embedded systems, more diversity of sensors, more increasingly sophisticated sensor processing, and yet there's no open standard for driving sensors and camera subsystems. And increasingly this has become a real friction point in the embedded industry. And so by popular demand, we now have the Khronos working group. This is still working on their 1.0 spec, so we haven't shipped a spec yet, but there's regular meetings to get the version 1.0 of the spec designed. As the stack shows, it's an application-facing camera system runtime API designed to be OS portable and portable across multiple types of camera hardware. You would have design templates that describe what are the streams that are available, what color formats would be used, what processing steps are available, and controls that are exposed on those templates to enable the application to control how that camera processing is undertaken. And we're trying to leverage the Vulkan design principles wherever we can, for example, resource management and synchronization would use the Vulkan models, which are well proven now. And this too, Khronos is relatively close to the hardware. So Vulkan is a good starting point for the Khronos design. OpenXR, I know you've talked about this morning, but for the record, OpenXR is a portable API for accessing XR hardware. Before OpenXR, you had to code to different APIs for each XR hardware. Now there's a common API that everyone has agreed to implement. And the good news for everyone, I think, is OpenXR, of course, is now very widely adopted. So good for the software developers who don't have to port to multiple hardware. It's good for the hardware developers because they get access to a larger ecosystem of software that's compatible with their hardware. And of course, it's good for the end users because they know that the applications they want will be available on the XR headset that they've purchased. And again, the strength of OpenXR is it really everyone who's shipping XR hardware is now adopting OpenXR, including the most recent announcement, Magic Leap 2 headset now is conformant to OpenXR. And these native APIs like OpenXR and Vulkan are being used to bring 3D and XR capabilities into the web stack. So W3C, the World Wide Web Consortium, is the standards organization that is responsible for the web stack. And so Khronos and W3C work very closely together. So WebGL was layered over OpenGL-ES. The new generation web 3D API, WebGPU, is going to be layered over Vulkan, as well as Metal and DX12. And WebXR, which is the XR standard for the web, is layered over OpenXR. So I think this is a good example of standards organizations working together, Khronos looking after the native API level, and then the W3C taking those native APIs and bringing them into the web stack. And so if you take all of these standards, it is kind of interesting. You have everything you need for what we call the metaverse, the immersive 3D environments, potentially in an XR environment, using cameras for pose estimation and semantic understanding, user interface, that might use Khronos. All of the vision processing and inferencing that you need will be done by the compute APIs. OpenXR, of course, for driving the hardware, with Vulkan driving the 3D graphics into the headset, with GLTF providing the assets that you need in your environment. So we do find a lot of interest in Khronos APIs for XR and metaverse type applications. And that's why, and the final couple slides here are on the Metaverse Standards Forum, which is now a separate organization to Khronos, but Khronos has initiated and bootstrapped the Metaverse Standards Forum because people were coming to us wanting to use our standards for the metaverse, but the metaverse is bringing together multiple technologies, Web3, inferencing, AI, as well as the GPU processing. And so we found the need to communicate and cooperate with dozens, if not hundreds, of other standards organizations working in their own areas. And the Metaverse Standards Forum is a venue by which all those standards organizations can cooperate and communicate with the wider industry. And we founded the Metaverse Standards Forum in June 2022, and Khronos has been funding the forum up to very recently. And in April 2023, just actually 2 or 3 weeks ago, Khronos has successfully transitioned the forum now to be its own standalone nonprofit organization. And we're already seeing the forum providing value in enabling different standards organizations to coordinate and cooperate and gather input and requirements from the industry. The forum is not another standards organization. It's a place for these different standards organizations and the industry to communicate. If you're interested in the metaverse, it's very easy to join the forum. There's a free participation level, or you can pay a modest fee and get to participate in the management of the forum. And we have a number of working groups, including XR, interoperable assets and avatars, geospatial digital twins, as well as Web3, governance, safety, privacy, security. So it's quite diverse. It's a broader remit than Khronos. Khronos has a focus on the acceleration APIs, but the forum is the way that Khronos and many other standards organizations can communicate with the broader industry. So that's a brief summary. Hopefully that was useful. So any company is welcome to join Khronos, of course. We are an open organization, and any company can join, get a voice in a vote in how any of these standards evolve. There's some links here. Also the Metaverse Standards Forum, where Khronos is proud to have initiated the forum, and that is also welcoming to any organization that wants to join. So hope to see you either in Khronos or forum working groups. Thank you.
Hello, my name is Tom Olson. I work for ARM. I'm chair of the Vulkan Working Group and former chair of the OpenGL ES Working Group. The Vulkan Working Group has been meeting here in Osaka for the past week. We're delighted and honored to have that you've chosen to join us and hear what we have to say. I have no slide with the program, so we're going to start with, from me, an informal update to what is happening in the world of Vulkan from the chair's point of view, and then we'll have more technical presentations from other speakers. So I'll start briefly. I always start my talks by saying, what is Vulkan? Even though you know. It's because a level set is useful, and Vulkan is actually more than one thing, and it is kind of useful to point out some of the non-obvious things about it. So I'll do what is Vulkan. I'll talk about where Vulkan is, what is new in the world, and then I'm going to spend about half my time talking about pipelines and state management. Hopefully I don't steal all of Chris's talk, but maybe I will. The reason I'm going to talk about that, pipeline creation and state management, we think, is the #1 problem for developers using Vulkan today, in the sense of the API functionality. And we've been working on it a lot, particularly Chris has been working on it a lot. And I want to talk about some of the solutions. We've been through a series of solutions, and I want to talk about that. So, as I said, Vulkan is not just one thing. You certainly know that it's an API. Specifically, it's a modern graphics and compute API for GPUs. It is similar to, well, it's descended from Mantle. It's related to, therefore, a cousin or a brother of DirectX 12, related to Metal as well. It is descended specifically from OpenGL and OpenGL ES. From them, it inherits being radically cross-platform and trying to go beyond them to bring together desktop and mobile. It's designed to give developers flexibility and full control over the GPU so that they can extract all of the GPU performance. The price of that is that it is complicated, much more than its predecessors, and it makes developers responsible for many things that the older APIs used to do for you. In terms of functionality, it's similar to OpenGL and OpenGL ES, but the design philosophy is quite different. In OpenGL, you get a high-level abstraction, which is single-threaded, synchronous, much simpler than the underlying GPU. Supporting this abstraction with reasonable performance requires a complicated driver, which does many things like dependency tracking, memory allocation, context management, synchronization, many other things. It makes writing applications relatively simple, relatively. But the driver is very CPU intensive and hard to reason about. And because the driver doesn't know what the application is trying to do, it has to guess. And when it doesn't guess right, things go sadly. In Vulkan, you get a rather messy and ugly abstraction, which looks much more like the underlying hardware. Most complex functionality moves out of the driver, which means the driver can be, again, relatively small and simple and predictable, easier to reason about. The price of that is the application has to do a lot of the work that the older API driver used to do for you. The advantage is that since the application knows what it's trying to do, if it is carefully coded, it can do a better job than the driver would have done and get better performance and lower power. There's another name besides API for something like that nice clean driver box on the bottom. We call it a hardware abstraction layer, or HAL. So that's another way to think about Vulkan. Vulkan is a HAL. It turns out that it plays a very important role as HAL for the GPU, because it makes it possible to write GPU-independent drivers for other APIs. And this is happening in the world today with OpenGLES runnable on some mobile devices through Angle, which is a software translator, desktop GPL running through Zinc, and there's a large, important commercial market using DXVK and VKD3D to run DirectX games on top of Vulkan. Now you might look at this diagram and say, why would anybody layer like this? Surely the performance will be terrible. Surely it will be awkward. But in fact, because Vulkan is such a thin abstraction, performance on these implementations is very, very close to native. My boss isn't here, so I'll say this. I know for a fact that although ARM's OpenGLES driver from Mali is on average faster than Angle, there are many games for which Angle is faster. It's a wide distribution and the means are much closer together than the standard deviation. It's quite impressive, the performance that Angle gets. Another way, a third way to think about Vulkan, it's an ecosystem. If you just start with the Vulkan spec and the library and the C compiler, you have no hope of producing a functioning Vulkan application. You need to engage with the whole ecosystem. So of course, there are the specifications, both Vulkan and SPIR, and various artifacts that derive from them, such as conformance tests and validation layers. There's a long list of software tools you use to work with the language. There are debug tools, performance tuning tools, and equally important, there's information and support, resources you need to help you use Vulkan. First among these, and most important, I would say, the Vulkan SDK from LunarG, which provides the tools and information you need to create a development environment. So that's what is Vulkan. Turning now to talking about some news, and I'll start with adoption news. Oh, sorry, I have this is a bug in the slides. This slide is about Vulkan adoption in the ecosystem. So Vulkan is adopted across all of the major commercial GPU vendors with one exception, and that would be Apple, who are a closed platform and a vertical and have their own GPU, which does not support Vulkan. In terms of platforms, we're supported on Windows, obviously, Android and Linux. We were on multiple game streaming platforms. Sadly, Stadia is no longer with us. We miss them very much. They did awesome work, and we learned a lot from them. It's supported on consoles, but specifically Nintendo Switch. And it is actually, even though Apple does not support Vulkan, there is a solution for running Vulkan applications on macOS and iOS, which I'll explain in a minute. And then, of course, there is engine support. All the major modern engines have paths for using Vulkan to render. Applications, of course, games were the driving use case for Vulkan, and there are tons of them. We used to be able to count, but we can't anymore because developers no longer make a big deal out of it and advertise it when they put a game on Vulkan. There are lots. In mobile, most of the big commercial high performance games will use Vulkan, at least where it is clear listed and known to work well. There have historically been a lot of bugs in Vulkan and mobile, and so most game developers check and make sure that the game is tested before they're willing to use it. Lots of applications that is non-game applications. Adobe Premiere Rush is a video editor. Adobe also has recently started to move various Creative Suite applications to Vulkan, including Substance 3D Stager. This runs only on desktop because it uses ray tracing, has a full-up path tracer in it that is based on Vulkan ray tracing where supported. Autodesk Fusion 360 uses Vulkan specifically because Vulkan is cross-platform and they need to run on Linux, Windows, Mac OS, iOS devices. And it's easier for them to maintain a path through Vulkan than to maintain separate backends for each of those. Turning to adoption news, I'm very grateful to Google that they do keep detailed statistics of what is supported on Android. So you can see that we're now up to the point where 85% of Android devices using the Play Store have Vulkan of some flavor, and the vast majority of those are Vulkan 1.1. So that's very gratifying to see. I did say I would explain how you run Vulkan applications on Mac OS. There is an open source shim layer called MoltenVK, maintained by the Brenwell group, that translates Vulkan calls into metal calls. It supports a subset, doesn't support all of Vulkan, but it's a carefully documented and well-supported, well-tested subset. The news on the MoltenVK front is that it is now up to Vulkan 1.2, which is great news. I should say also that the LunarG SDK fully supports this path. So this is not some sort of cheesy open source project with no support. It's not a hobby. It's a real commercial enterprise. And the proof of that is that there is a lot of content, including commercially very important content, running on top of Mac OS and iOS using this path. Other news, we have a number of initiatives concerned with getting information into developers' hands. In February of this year, we hosted a developer event in Munich, Germany, Vulkanized. We've done Vulkanized events in the past. They have been mostly like this one, rather small, 5 or 6 hours, single room. This event was something different, a 3-day conference with an open call for papers. More than half the content was provided by external submissions, and 180 people attended. We found it very successful. The people who attended said it was great. So we're very interested in doing this again in 2024. Probably not in Germany. We want to move around the world to reach more developers. We have a project aimed at improving Vulkan documentation. The idea here is to bring together the specification, the manual pages, the Vulkan guide, and various other resources that we have, which right now are sort of scattered across multiple repositories, bring them all together in one place and connect them, link them together. This is work in progress, but we have a demo up at this URL, and we would love to have you go try it, kick the tires, see if it works. If you find issues or if you like it or don't like it, please let us know by commenting on the Vulkan Docs repository on GitHub. That's the specification repository. We hope to build this out and include more. Right now, it just includes the guide and the specification, but it shows what can be done. I want to mention something a little quirky, something we have not done yet, but are thinking about. This is an idea of Shabazz Yousefi from Google. Since Vulkan implementations do no error checking, the specification is very careful to document the rules for correct use of the API. So if you read the specification, it's full of blocks of text like this that list the valid usage rules that an application must follow when it calls an entry point or fills in a structure. These statements are all written in English by us and then translated into, we are human beings and we make mistakes. They are also translated into code in the validation layers by human beings who have issues interpreting them. So there are a number of problems. We find them confusing, we in the working group. And if we find them confusing, we assume it's worse for people who are not members. So the idea that Shabazz had was, suppose that we express these in a more formal language. And this is, animation bug. Instead of writing valid usage rules in English, like the upper example, suppose we wrote them in a formal language, such as code. So Shabazz, we've been discussing this for some months, and Shabazz has convinced us, I think he convinced us at this meeting, that indeed, these are easier to read if done carefully, and possibly less error prone to write. They're also machine readable and perhaps machine checkable, although there are many issues with making that happen, but it's an intriguing idea. So we're not committed to this, but we're very interested in it, pushing forward. The proposal for this is public. It's on GitHub, Khronos Group, Vulkan Docs, in a pull request. And we would love to have people look at it and tell us, that is, have developers tell us, does this make sense to you? Do you think this would be better than what we have today? In the SDK front, there is more news than I could tell you. Karen presented at blinding speed for 45 minutes in the course of the week's meeting, and I could not even begin to do justice to all the work that is going on there. I do want to particularly mention major advances in synchronization validation. The phase 2 covers multiple command buffers and multiple queues and synchronization between them, which is a huge win. There is better runtime validation, and there's validation performance improvements. Profile tooling is beginning to be used. There's a major project underway to change the way descriptor validation works, because our descriptors are so dynamic now, the old ways don't work anymore. I did want to highlight the amazing number of SDK downloads that happen. 35,000 Windows SDKs a week blows my mind. Okay, that was my talk on news. So I have completely skipped what's new in the API because there wasn't time. I will get to one or two things that are new. I want to spend the rest of my time talking about pipelines and state management. As I said, we've known for a long time that this is a big problem for developers, and we've been working on it for a long time. I believe it was 4 years ago we started the pipeline. 3 years ago, the pipelines TSG run by Chris with the glasses on his head there, and they've been doing a series of things to make the situation better. The work's not done. We see this as an ongoing project, and we just agreed that it's going to become a permanent effort as opposed to a allegedly temporary effort. But we do have progress to report. So quick reminder, in older APIs like OpenGL, you draw relative to a context, which contains all of the state of the graphics pipeline. And you call a function on the context to change a piece of state. So your application render loop is set state, draw, change state, draw, etc. In Vulkan, you don't have a global context. Instead, you have command buffers. And you put your drawing commands into command buffers instead of issuing them and dispatching them to the context. And you can create those command buffers in multiple threads. And you submit them later after creation. Instead of setting state directly on the command buffer, though, you set it on objects called pipelines, which bundle together all the information needed for a draw. So your render loop is now different. It's bind pipeline, draw, 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 bind pipeline, draw, 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 and so on. And this is fantastically lightweight, provided you are able to create those pipelines and have them ready to go in advance. Why does Vulkan do this instead of doing what OpenGL did? Well, as I said, Vulkan can be thought of as a hardware abstraction layer, which hides, or tries to hide, some of the differences between different GPUs. Presents the hardware as a pipeline with the same stages, essentially, as the OpenGL pipeline. There's input assembly, vertex shading, etc. And then that has to run on the hardware. And real hardware is also a pipeline, but it is not the same as the Vulkan pipeline. It is nowhere near as clean, and every implementation is different. The only guarantee is that there is a mapping from the nice, clean, relatively clean Vulkan abstraction to the underlying hardware abstraction, and managing that is the job of the Vulkan driver. Before the hardware can execute a draw command, the driver has to translate the state from the Vulkan pipeline into the state for the hardware pipeline and install it. Unfortunately, the hardware pipeline being quite different from the Vulkan pipeline, hardware pipeline state depends on Vulkan state in very complicated ways. The result is that you can make what you think is a very small local change to the Vulkan state and find that it changes everything on the hardware side, and that essentially the driver has to start over and build a new pipeline from scratch. That is very CPU intensive, very expensive. If it happens in the middle of a rendering loop, you're going to probably drop a frame and your user is going to be very unhappy. So the Vulkan solution for this is pipeline objects. You ask the application to put all of the state needed for a draw into a pipeline object and to create it early outside the render loop. To make creation faster, Vulkan also provides application managed caches. So in theory, you never create the same pipeline twice, and those caches can be saved to disk and read back. Also turns out that some state can be changed quickly. Some Vulkan state is orthogonal. And that state, Vulkan allows to be what we call dynamic, which means that it is set on the command buffer rather than being set in the pipeline. But the application has to opt into that because there is usually some cost, even if it's very small, to setting that state dynamically. So that's how Vulkan, classic Vulkan 1.0 worked in 1.1. And sometimes it works very, very well. And there have been applications, famously Doom Eternal, which were able to get down to something like a few hundred pipelines, which were created all in advance and ran screaming fast because they did no work in the render loop to manage no driver work. Unfortunately, it doesn't always work that well, and there are many applications which have been unable to do that. Sometimes you just don't know what state combinations you're going to need until you need them. And sometimes you need an enormous number of combinations. That means you have to create pipelines during command buffer recording in the render loop. The cache helps, but it doesn't help enough. With the cache, you may not know, so you call create pipelines, it's unpredictable. It may be super fast because you get a cache hit, or it may take 200 milliseconds because you took a miss on a really ugly pipeline. So what do? We've done a number of things. Our first approach was simply to increase the amount of dynamic state. In Vulkan 1.0, we simply took what was very easy to do, and we've added a series of extensions, dynamic state 2, dynamic state 3, and also vertex input dynamic state to make more and more state dynamic. Not all implementations can expose these. So extended dynamic state and dynamic state 2, I believe, yes, they are core now. But in dynamic state 2, some of the features are optional, that we left them out of core. But there are some optional features there. And then in extended dynamic state 3, my understanding is it's all optional. So it's simply a language for the implementation to tell the user, these are the things I can support dynamically. So that was one set of fixes. Another set of fixes is to make the pipeline cache more usable. These ideas mostly came from the Stadia team, and they were very good, and these are in core as well now. Pipeline creation feedback simply allows you to find out when you create a pipeline whether it was already in cache or not. Many people, especially systems like Stadia, which have share a lot of data between instantiations of the server, try to pre-populate the cache so that even the first time a new user plays it, the cache is already full and they don't have any pipeline creation happening. But in order to do that, you need a way to make sure and validate that your cache contains everything it needs to. So pipeline cache feedback gives you a way to determine at runtime if you have a problem with your, if your cache is not fully populated. Pipeline cache control is different, rather interesting. It lets you tell the driver, here's a pipeline. If it's in cache, please give it to me. But if it's not in cache, just say no and return immediately. Don't spend any time. Don't make me wait, and don't make me drop a frame. So what happens is, the way this is intended to be used, your application has a new pipeline. It doesn't know if it's new. It says, give me this if it's in cache. Otherwise, give me null. And if the driver comes back and says, no, this is not in the cache, then the application can find some other path, such as it might have a prepared pipeline for a big, huge Uber shader, which runs slowly, but it can draw absolutely anything. So you use that as a fallback. And in the meantime, you have a server thread, which goes and compiles the pipeline you really wanted and gives you a fast version back. And when it's ready, you switch it in and use it. This way you get no stall and you lose some GPU performance briefly, but it works much better. And there's a brilliant blog by, actually, I think I have another slide on this. No, sorry. There's a brilliant blog. No, I'm wrong. Apologies. The brilliant blog is about this one. This is work this was published somewhat more than a year ago, Graphics Pipeline Library. This takes the idea of pipeline cache control and fallbacks and runs with it and makes it more institutional and supports it better. So the idea is that we break the pipeline into segments and we allow the application to create mini pipelines which handle only a subset of those segments. So they may be complete or they may be partial. So you create partial pipelines for subsets of the groups. And when you need a pipeline to draw with, in the render loop, if you have a new combination of state, you can take the various partial pipelines and ask the implementation to link them together, give you a pipeline, but to do it very fast. So don't optimize across them, just glue them together as quickly as you can, give it back, and that's your fallback shader. But instead of being a generic Uber shader, it's a fallback which is closer to what you really want. Then you can start rendering with that. And in the meantime, you can, again, on another thread, tell the pipeline library system, now please take those same libraries, those same components, and give me a highly optimized shader that will run really fast. So that happens asynchronously. When it's ready, you switch to using it, and you're good to go. So this was released a little over a year ago. It's very difficult to implement. It's a lot of work, and to date, as far as I'm aware, it's supported only on AMD, NVIDIA, some Mesa drivers, and some Qualcomm drivers. But we all believe in this. That is, all of us IHVs, we're working very hard to implement this, and we do expect that this will be supported everywhere. There's a good webinar by Chris explaining how it works, and there's a good blog by Dan Ginsberg from Valve explaining how he eliminated draw time hitching from the Source 2 engine by using this technique. There's also sample code in the samples repository by Sasha Willems. So we have high hopes for graphics pipeline library, and we look forward to when it is universally available. But it may be possible to do better. And so I hate the way this thing scrolls. Just a few weeks ago, we released the XT shader object, which takes us, in a way, almost back to OpenGL in terms of a programming model. Instead of creating pipelines early, you create individual shader objects early, which contain the shader for a single pipeline stage. All state is dynamic. No state is set in a pipeline. There are no pipelines. No state is set on the shader objects. So your render loop becomes bind shaders, set state, draw. That's all it is. And it's, if you think about it, a lot like OpenGL. So you may be asking, if it's like OpenGL, how can it possibly be efficient? Well, I can tell you that on NVIDIA GPUs and on the Nintendo Switch in particular, it is efficient. It works very well. And those are the only platforms that currently support this. We have thought about this and discussed it a lot, and we think there is hope for this or something like it to be efficient across the whole industry. But we have not solved those problems, and we have not proven it out. Many of us, including ARM, are planning to do experiments with it, but we don't know if it's really going to work. My understanding is, at least our internal discussions are, you won't see implementations on any GPUs other than NVIDIA before 2024 at some point. And some of those implementations will be experimental. Still, it's promising and interesting. So you might ask, gee, you have 7 different ways to deal with pipeline creation. What should I actually do? Please give me some advice. I'll give you my advice. I'm not a programmer first, so take it with a grain of salt. But this is my belief about the state of play. First of all, if you can use classic Vulkan, if it works for your use case and your application, absolutely use it. Use pipelines and use static state. It is guaranteed not to be slower than anything else you could do. On some implementations, it is going to be the only fast thing. That said, if you use entirely static state, you're probably going to be creating a lot of pipelines, and that could cause you performance problems by itself. And if you find yourself in that situation, the number of pipelines is exploding, by all means, use dynamic state. To date, so far, we IHVs have been very good about not exposing something as dynamic unless it really is fast. I don't say it's cost-free, but it is probably better than creating multiple pipelines for each possible set of states you want to use. So dynamic state, highly recommended if it's there. Graphics pipeline library, when it's available, by all means use it. We all believe in it, I believe. Somebody may hold up their hands and tell me I'm wrong, but I believe we in the working group all think this is a great solution and well recommended, again, if it works for your use case. I do want to say, if you use it, do not make the mistake of saying, well, I've created this fast, quick linked pipeline, and I know it's not very efficient, but I'm too lazy to go compile an optimized pipeline, so I'll just keep using it. Please don't do that. Please to create an optimized pipeline. That is the intent of this extension, and that is how it should be used. And then finally, if you only need to target switch, obviously you should use shader object. It will work very well for you, and it's very convenient to use. If you're only targeting NVIDIA, same deal. Watch this space. As I said, it's going to be a year perhaps before we have a clear idea of how this plays out on other architectures. But there is hope. You know, we've done the analysis. We think this can work potentially at some point in the future. So watch the space, but don't start a commercial project which depends on it arriving, because we don't know when and if it will. That is all I have. I apologize. I took way more time than I was supposed to.
Hi, my name is Hai. I work for Google, but I'm here as an independent person today because this is presenting you a hobby project. This is kind of like my gift to you. So I've been experimenting with ray tracing on both APIs, Vulkan and D312. And I've learned a lot, and I wanted to share some of this knowledge with you. It's a really quick talk, maybe an in-depth version for a later time. But if you are going to start experimenting with ray tracing, you'll hear a bunch of things like procedurals and instance IDs and what else? Or just there's a whole list of terminology, and it can get really confusing really fast. And so what I did was I just went through and I started at the very top with Sasha's demo, ray tracing demo, and I started kind of working my way up to support the advanced topics in ray tracing. So this is what I'm gonna walk you through my little journey of it. And the code for this is 100% available online as of right now. It will break because it's an experimental project, but I'll leave the link up at the end. But so the first thing that I had to prove to myself when working with both APIs was to make sure that the coordinate systems were the same. And so, nice UV plot to figure out where the U and the V are. That's D312, and this is Vulkan, and it's the same thing. The next thing was, obviously like doing the triangle test, like can I ray trace a triangle with barycentrics? Pretty easy. And there it is. The color is wrong because the swap chain swizzle is wrong. I didn't realize that until earlier today. And then there's this thing, there's the procedurals inside of ray tracing, which they don't get a lot of tutorials, but it's basically if you want to intersect like, boxes or spheres or whatever instead of having real geometry. So, I started with the sphere because it's the most basic procedural, D312, and then Vulkan. And then I think everybody here has seen some version of this. It's Eric Haynes' Sphere Flake. And this is all running in real time, by the way. It's not, I'm not clicking on a bunch of pictures and showing you that. It's not interactive yet. We'll get to interactivity soon. So that's D312, and this is Vulkan. I'm just going to show the Vulkan version from this point on. Hopefully I've proven to you that both APIs are working the same. And so, the thing you do after you do the Sphere Flake is reflections. And this is, I don't know how many it is, but some ridiculous number of spheres in there, and it's bouncing all around, and I'm running on a 3070. And there's, I think I set the recursion at 5, so it's a bunch of stuff going on. And once you got reflection going, obviously you're gonna want some shadows, nice ray tracing shadows, pretty cool, right? And then of course, when you show it to your friends, the first thing they're gonna ask you is, I wanna see it move. Okay, fine. So let's make it move. Ray tracing, right? Animated ray tracing, real time, pretty cool. Also kind of amazing that you can do this on a laptop, because 10 years ago, this would have been impossible. I mean, you would have waited for hours for this thing to render. Maybe not hours, but depending on how rich you are and how big of a machine you had. Okay, so So those are all procedurals. There's no geometry there, which is kind of cool because then you realize you can do things like volume tracing and all this other stuff that you find in the classic material of ray tracing. So, but what if you want to do some triangles? So we go all the way back to the beginning, and so oops, clicked on the wrong one. So all the way back to the beginning, and we ray trace a triangle mesh. So triangle mesh, and then you encounter this thing. There's this thing called, well, can I get the geometric ID? So when you're building acceleration structures, ray tracing, you have the most basic primitive you have is a geometry, and then but it's maybe when a ray hits this piece of this object, you want to figure out which geometry it is, and so there's a function in both GLSL and HLSL that lets you figure out which one it is. And so this little demo doesn't do anything more than just lets you figure out which piece of geometry it is. So this is 3 pieces of geometry, but the more used one is the instance ID, since it's a little bit more obvious. So, and with ray tracing, you have 2 levels of acceleration structures. You have your the bottom level, which is where all your nice geometry goes, and you have the top level, which you can only have one of. You can have as many bottom ones as you want. The top level one, you don't have one of, but you can have a bunch of instances inside of the top level. And so you want to be able to hit the instances as well as the geometry. It's more supported. So, and Tom earlier mentioned that, well, okay, I would have shown you this, but I don't have the Vulkan version, so you're looking at the detail version. I'll get the Vulkan version soon, but this kind of explains probably why you wouldn't want to do everything in ray tracing, even if you can. This is a PBR GGX grid that everybody has seen. It's really slow. It's interactive, but it's super slow. So I'll move the mouse for you. You can kind of begin to see like why you probably don't want to do it. So there's no cheats on this. This is all being sampled with crazy numbers of rays, etc. Not very practical. So Tom mentioned that Adobe implemented a path tracer. So what if you're staying at home and you're bored and you're like, well, I want to implement a path tracer in ray tracing. What do I do? How do I do it with Vulkan on the GPU? Well, I have an example for you. And so you start out by doing a very basic path tracer, and it's path tracing some spheres. There's in the sample you can change it to a knob or a teapot. And again, it's interactive. You rotate it, and everybody's seen some version of this, right? Like it's nice, but this is about like 400 or 500 lines of shader code and probably like 3,000 lines of API code, and it takes a lot of setup. But once you get it, it's pretty awesome. The ray tracing. This is where ray tracing gets a little fun, because you can kind of begin to produce these like crazy cool images that are really hard to produce with just straight up rasterization. And then so you got this, and the next step is you're like, okay, I want to go one step further. What if I want to add PBR to my path tracer? This one isn't PBR. It's just like a simple dumbed down, like, I don't even know what it is. Actually, I forgot what I implemented, but it's a simple lighting model. Let's just go with that. All right. So you go and you find some material, and you spend weeks trying to break apart the GGX equation of how to implement it into like a brute force path tracer. And then you fire up your demo and get a bunch of SPIR-V messages that looks kind of embarrassing, but I don't know why this is happening. Just give it a second. Anyways, this is what I wanted to show you. All right. So you now you've implemented a pretty cool, pretty robust lighting GGX based path tracer, right? And it's path tracing. It's a little slow, but again, it's even crazy that you can do this on a 3070 in real time. And to prove that to you, I can just rotate it around right here. I can also lower the number of samples where it stops at. And the other thing is, you done a good job, and your lighting model is pretty robust. It can respond to all the lighting conditions. And again, you can rotate it. And so you learn a little bit about rendering. This is what the sun looks like at high noon. This is the worst time of the day to take a photograph of your loved ones, because it'll look terrible. So don't do that. But there's some some really spectacular spots, and that's because of the high frequency between the sunlight and the rest of the sky. but you're like Travis, you're into photography, so you know that the best time to take a picture of someone you like is probably at golden hour. And this is a very uniform light distribution, so it converges really quickly. So after just a few seconds, you can kind of see to get really smooth because there's uniform lighting. And yeah, so it's real time. And you can flip between these things. All of these, so all of these things in this demo are free. The licensing for a lot of the textures is from Polyhaven at CC0, so you can kind of do whatever you want to with it. The knob is from Filament, the monkey's from Blender, and anything else I probably made it like this little weird box here. I did it to kind of prove some of the anti-aliasing, but so all of this is right now available on GitHub, and this is the URL right here. You can go and download and play with it. Both APIs. It's have fun like I did. All right, well, enjoy.
皆さんこんにちは。Vulkan validation layer 効果的な仕様です。Actually, I'm kidding. This talk is all going to be in English. Don't worry. でも、日本語バージョンのスライドを作成したので、ファウル中に、ファウルしたい方、利用ください。And so, yes. We'll wait a moment for some people to get some photos. Hi. Okay, so yes, welcome to using Vulkan validation layers effectively. So my name is Spencer Fricky. I work at LunarG. I've been working on the validation layers for about 3 years now. So I would feel confident I can talk about the validation layers. It's currently my main task at LunarG. And before we get into the validation layers, we should talk about Vulkan layers. So Vulkan layers, hopefully if you've worked with Vulkan, you've seen this system of having the app, the loader, the layer, and then the GPU. So we're gonna be working on the yellow box in there. So what are the validation layers? Well, they're just a Vulkan layer, but they're used for error checking. Vulkan does not have any error checking in the drivers. It is gonna be done all on this layer. And the nice part about doing this is at development time, you can do all the validation. And then when you wanna ship your application, you can remove the layer and then not have to worry about the overhead. So why we have the validation layers is because OpenGL didn't have it. And the two main issues were, well, the first issue is that every driver has to do the same error checking. It's a lot of duplicate work for every driver. And when you knew your OpenGL code was valid, you still had to pay the cost of validation. So now with Vulkan, we don't have to do that. We have this layering system. A common thing we get asked is, why is it the Vulkan validation layers, plural? Historically, there were many layers into this one, essentially mega layer. We turned it from multiple layers to a mega layer. It reduced a lot of code duplication. And now the mega layer, which you now know as the Vulkan validation layer, is broken up to many sections, as we'll get into later. First thing we need to talk about is a VU. We use it all the time in the working group meetings, VUs, but then I realize not everybody understands what that means. It's a valid usage. So the whole idea of a valid usage, it's the rules in the spec that define what you're not allowed to do. And the drivers assume you're not doing it. And if you do, that's undefined behavior. And with undefined behavior, anything is possible. And this is a common misconception. You do something invalid, it works, and then you run on another GPU and it blows up. So we try to avoid the undefined behavior, but sometimes you get lucky. So these VUs all have VU IDs. They're just identification numbers. It's a nice system. That way you know which VU we're talking about. We can point it back to the spec. It's all generated. There are a few unassigned views in the validation layers. That just means we haven't got around to properly adding them in the spec. But for the rest of them, you'll see in the spec, you'll see a section right here with the valid usage. These are the VUs for, in this case, for VK create buffer. And each of them is given a nice VU ID. And then below it, this one confuses a lot of people. There's an implicit valid usage. So this is all, the best way to describe it, this is all generated stuff. So this is you making sure you're not passing a null handle. If you have an array of elements, making sure you actually have those elements in the array. All this stuff, all the implicit ones are generated, but they're just as the other ones. If you break them, it's undefined behavior. And the best way to distinguish the implicit VUs from the explicit VUs is just noticing that there's no number on the implicit ones. So that's how you can quickly distinguish which one's which. And all the HTML has these nice anchor elements. So at any moment you can append to the spec URL if you're viewing it on the website, and it will drop you to the correct spot in the spec. So really quickly, want to talk about these conditional VUs. These are a cause of confusion. So there are times where the Vulkan spec has to add new extensions. And in adding new extensions, we get two VUs that are logically doing the same thing, but they're different. And in this case, this extension added a new enum. And so this new enum was not there before. So if you build an older version of the spec without the extensions, this will not be there. And if you build it with the spec, you'll see the top one instead. And in practice, what this does, it looks like, is if you take the URL, Khronos provides 3 versions of the spec, one with all extensions, one with just WI extensions, and one with no extensions. So sometimes people, come confused why they can't find the VU in the spec. My suggestion is just to try either appending or removing the extension version of the spec. So these VUs have a very they have a life cycle, and the idea is that every time there's a new extension, there's more VUs. Sometimes we get spec bugs saying that this should be a VU, and we think, yes, you're right. And then we create a PR for the spec. It gets added to the new version of the spec that gets released, and then the team at the validation layers, we implement it. Simple. But then come along a new extension, and it overlaps with an old extension, which then causes a variation of VUs. Sometimes they conflict. You get those weird conditional VUs, and just sometimes we have spec bugs and a VU is wrong, and they get fixed as well. After that, same process, create a PR, the VU gets pushed into the next release of the spec, and then we go ahead and fix it. So this is how VUs operate. It's not too complex of a system. So what kind of validations and VUs are there? The main two, there's kind of 2 of them, but the main one is probably just API usage. And this is a very simple case, but if you have trying to create a 2D image and you set it with some depth, it doesn't make any sense. This is undefined behavior. You might get lucky. I don't know what you expect to happen, but this is something we catch in the validation layers, and this is just using the API incorrectly. What's a little bit more trickier is what I call environment validation. So if you set your color attachment count to 5, you might run on your machine. It might be perfect. And then when you push it off to another device that only has the minimum required 4 max color attachments, it will fail. It's undefined behavior. The GPU doesn't support it. So this one, there are techniques to get around this. One is just testing on many devices. There's the profile layers. But yes, this is a harder one that can catch you off guard. So let's look at an example of validation. So this is the VK cube. The VK cube is just a simple, hello world style cube inside the SDK. And we do a buffer to copy buffered image. So we're trying to take the texture here and take a memory from the buffer to texture it on the image. In this case, we're gonna extend the buffer length by 2, which results in an error, these weird artifacts. And then this is the error message you get. A quick side note is there's a yearly developer survey that goes out, and we do take that seriously. One of the big things we were told this year was, and the year before, where these error messages are a little not fun to read. And I understand that, and it's been a priority of the validation layer team recently to improve this. But I'm gonna break this down to improve that's not as scary as it looks. So the first thing you do is you get the basic info, such as this is an error. So there are warnings, and we'll get to later, but this is an error, says it right there. And then this is the VUID we were talking about. So this is then tells you what part of the spec you broke. And then you might see these message numbers and message IDs. These are just hashes of the view ID. The view ID is a string, and we want to bring it into a faster machine readable format. So we hash it, and it's used for a lot of the settings, such as preventing duplicate messaging. So we print that out as well. Next is what I call the main message. This is the part where someone has more or less handwritten the error to, return it in a English friendly way, what's going on. The first thing we do is we print where the error happened, because sometimes you get a struct and you don't know what function called it. And then if you're inside, in this case, a P region, we want to let you know which P region it is, so you know which one to look at. And then lastly, this is our attempt to take the logic and put it into a little bit more human readable format. And so that's with the goal there. My biggest advice is to, if you get an error, fix one. The most common issue is people have 30 errors, and it's all because of the first error, because it just cascaded. So if you do ever hit an error, my suggestion is, or if you hit 30 or 40 errors in a row, just try to fix the first one. Most likely it will fix the rest of them. So going back to the error message, we do print there the Vulkan spec in the bottom of the error message. So this is what it looks like in the spec. Sometimes they format very well. So in this case, the spec is written in ASCII doctor, and there's a lot of code to try to massage the ASCII doctor to just plain text. It does fail sometimes, or in this case, you don't get to see the URL where buffer and image addressing points to. So in that case, we do give you a link, a URL to the correct version, either with or without the extensions. That way you can view it in the spec yourself. Next thing, and the last thing we're gonna talk about this message is the object handles. So this is a buffer, it's just in your command buffer, and is a buffer to image. So the image is not important here because the buffer was the error. So we print out the command buffer and the buffer that caused this error. And what's kind of hard, so the handles, when you create a VK buffer, it's really just a uint64 handle that the driver understands. So this is what that handle is. It's just that integer value being printed out. But it would probably be nice if you could, give it a name. And so this is where this debug utils extension comes in. The debug util extension, there was a original debug report and debug marker, but now I would suggest just using debug util. It actually implemented in the validation layers, so you have support. And the main task is to just give more human-friendly names to these handles. So when you use tools like the validation layers or even RenderDoc, it will give you those names and to make it easier to debug. So this is what it looks like. This is one part of it. It's just given an object name, there's a struct, and then you just set it. And again, this just allows you to give the proper name to each of these objects. So looking at an example, the first part, this is the struct. You obviously set the S type, is everybody's favorite thing. And then you set the object handle, in this case, what VK buffer I had. And then the object type, we have, there's buffers, command buffers, pipelines, images. You tell it what object type it was. And then most importantly, you give it your name. In this case, I gave it the name text buffer. And then in the bottom, you now see the error message, it provides the name. So this way, when you look at the error message, you'll get the name for you. But we can go one step farther. There's another part of the extension called labels. So same idea, labels, in this case, we're gonna use the labels in the command buffers. And so we give the label, pass it a name, there's a color fields, and then you set it, in this case, while you're recording your command buffer. And what this allows you to do at the bottom is see the various parts of the command buffer you got to. So if you want to know where you were in your command buffer before it all blew up, this is a great way to label that. And again, an English-friendly way. In this case, the validation layers will just print the colors out. But if you're using something like RenderDoc, it will provide the colors for you. So it's even nicer. And so yeah, this works as like a pop and push style. You can tell it when to start, when to stop. In this case, I just have 3 labels, nothing too complex. So going back to it all, now with the error message, going back to the error message, using the debug utils, I mean, it's still a wall of text, but it's a lot, but at least there's names now in it to help it make it more friendly of what's going on. So the debug util also has a third feature to it. There's this custom message callback. So when you get the error message by default, it usually prints out as just to std out. People do like to sometimes format their own error messages. So this part lets you, every time there's an error message, you can handle it yourself. You can push it off to your logs. If you have a server farm, you want to push it off to your logging system. So yes, or trigger failures in a testing framework. We do warn you not to use this to filter messages because we have, I'll show you soon, we have a faster way of doing it built in. So now that I convinced you to use validation layers, hopefully, where do you get the binary? My suggestion is get it from the SDK. And my other suggestion is always to grab the latest version. We constantly add improvements and fixes and enhancements. So the SDK is always a well-tested version you can rely on. But if you want to grab it from source, we have great documentation how to build it. And don't be afraid to try to build it yourself. And to enable it, it's just a layer. So there's a whole mechanism for enabling layers. VK config is the simplest. I highly suggest, but you can also at VK create instance time, set it. And if you feel very comfortable, you can use a terminal as well and set your environment variables. So if you're going to use the VK config, this is what VK config looks like. But on the right side is where the magic of VK config comes into, is when we have all these configurations. So as I mentioned earlier, the layers used to be many layers, that we have now one layer, and we split it off because if you try to enable everything, it becomes painfully slow. There's just too much validation to do. So we have this ability to break it up into different sections. And to set this, we have these nice presets. So the presets are nice. We try to give you strong ideas of which things to put together, but you can also set these via the environment variable file, the VK layer setting file, which we read in. You can set it with the environment variables, and there's also an extension to let you set it dynamically at creation time. There's a link that we provide all this information about setting these options. But now, what are all these options? And that's what we're going to talk about next. So the first one is stateless. Stateless is primarily generated logic. It's all those implicit VUs you saw before. They're very cheap to check because we don't have to track any state. It's just, checking the parameter values. The next is core. The best way to explain core, if it's not anything else, it's in core. Core is, I'm gonna say like 80%. It's just the base of all the validation that you would imagine it being. Thread safety is what we use to check when you're trying to use multiple threads on an object and you're doing it incorrectly. The biggest issue with this is it will destroy any multi-threaded application's performance because we have to lock and make sure you're not, trying to misuse threads on different threads incorrectly. Next is handle wrapping. So as I talked about before, when you create a VK buffer, you get that UN64 handle. That sometimes people do things such as handle wrapping, and you can get these nasty bugs by thinking you have the handle, but you actually have some other random UN64. Object lifetime just checks that you've remembered to destroy any objects, or if you try to double free or double destroy an object, it will catch it. There is shader base, and by shader base we mean we actually take your SPIR-V and modify it. And that's why we call it shader base. So the main use of this is GPU assisted validation. So there are certain things that we don't know until you run it on the GPU. We don't know what the value is going to be. Descriptor indexing is the poster child for this. If you have an array of descriptors and you want to index into that array, but you don't know until you actually run on the GPU which index, you might be out of bounds and have no way of knowing. So we take your SPIR-V shader, add a buffer to it, we take one of your descriptor slots, and we write out all the information to that buffer. And then when we're done, and you're done executing the GPU, we pull it off, we read it, and we guarantee that you didn't have any undefined behavior while you're running it on the GPU. But lately, there's been a new addition to this, and that's been the debug printf extension. So this is an amazing little extension that adds printf capabilities to your shader, and it works the same way, instrumenting your shader, and then taking the values and reading it off. As of right now, it's not supported on iOS. So if you're using iOS, I'm sorry. Next is synchronization. This has been a great addition to the validation layers. So there's a great thing on Reddit, how hard is it from OpenGL to Vulkan synchronization? And so synchronization's hard. You can get some nasty read after write type hazards. And this is what this is for. We'll do a lot of tracking to check to make sure you're not accidentally setting the wrong pipeline barriers or wrong access dependencies. And the next thing we're talking about is the best practice layers. So these were added a while ago, and the idea is sometimes things are not invalid. It's not going to blow up your machine, but we don't think that's what you want. So these are things like performance warnings, and we're going to do a few more examples in a bit. But lately, there's been a lot of vendors who've come out and have been adding a vendor-specific check. So there might be a chance that the vendors have certain things that they want to warn you about that on their implementation might not be the best. And so the best way to explain best practice is that there's sometimes in the spec, we say undefined values, which is not the same as undefined behavior. If your value is undefined, your app won't crash. You'll probably still get an artifact, you might be a bug, but it's not invalid. The driver won't blow up on you. A great example of this is that when you're going between a fragment and vertex shader, if you have in the first one on the left, I have 3 outputs, 3 inputs. Perfect. If you forget the output, that's an error. That's undefined behavior. But if you forget the input, you essentially have just written out data that no one's consuming. It's not invalid, but we don't know that's really what you wanted. And this is stuff that the best practices are going to try to catch for you. The stuff that's most likely a bug, but not going to blow up your machine. So those are all the parts of the validation layers. Next are the settings. We have this nice little ability to break. So once you hit your first error, we'll stop, hit a break point, depending on what operating system you're on, and hopefully let you debug it. In the past, we used to have this idea of, we used to mix the best practices with everything else. We've slowly almost got it fully separated. So if you're not using best practice, you only will have the error message. But if you're using best practice, we still split it up between performance, warning, and just a simple info. So this will let you filter that automatically for you. And then limited repeated messages. I've had this myself where you have an array of 50 items in your struct and they all are wrong, and then you get 50 angry error messages. And so this is a great way to reduce that message duplication. And this goes back to why we have those hashed view IDs. And then next, muting the message. Sometimes undefined behavior works and you're busy and it says fine, you're showing a demo, move on. And sometimes the validation layers have bugs. We try to fix them as fast as possible. So there's but if you do, please report them. We like to know about them. And then sometimes the spec has bugs. And when we realize the spec, we as validation layers are just following the spec. And then someone points out that the spec is wrong, which brings up the question, where do you report a bug? Sometimes it is a spec bug and sometimes the validation layer bug. First thing I'm gonna ask is that you do some due diligence and try to make sure you aren't just reporting issues for the sake of reporting issues. But I'm more than happy to take the validation layer issues and bring it over to the spec. But these are 2 different repos for 2 different parts of the ecosystem. And it brings up another great advice, read the spec early and often. The spec contains all the information you ever need. And as Tom put in his earlier talk, we have been working very hard to make the spec easier to search. Because we realize it's a large, huge spec. But if you're going to use Vulkan, I would suggest knowing how to navigate the spec is a very important skill set to learn. So when it comes to fixing the errors, another simple advice is just have a debugger, breakpoint, and figure out what you're doing wrong. But sometimes people still are confused. And so luckily in the validation layers, we keep all the strings as searchable. We don't try to do any fancy concatenation. So if you have a view ID and you want to look it up, you can just grep it inside the validation layers, and you can see the actual logic, the actual logic that we use to get it. So with all that, I gotta say there are some limitations. Mostly that the VUs have increased greatly And Vulkan came out 7 years ago, and there was about 3,000 VUs. There's about 18,000 VUs now. So it's about a six-fold, time multiplication. And sometimes, honestly, writing the validation is with these simple extensions, it takes just as long as writing validation for a slightly more complex extension. So it does take time to add extensions. We try to prioritize your KHR and EXTs as they come out, but there's still a lot of incompletes. And if you do find incompletes that you ran into, please submit issues. We find this very helpful when people report that they hit some error and we didn't catch it because we don't have it yet. We do appreciate that. And this is a graph to kind of illustrate the point how the top line, the yellow line, shows the number of VUs growing. The green line shows how many we have added to the validation layers, and the blue line shows how many are incomplete. The blue line should be flat and going down, but lately it's been, as extensions get added, it's been going up and up. And so it's another part that we're constantly trying to fix. It's an ongoing battle. And sometimes these VUIDs are just hard. There are certain VUIDs, especially around descriptor indexing, that will take weeks just to get 1 or 2 done because they involve a lot of testing, a lot of checking, and you don't want to be. We try to eliminate as much false positives as possible, and so this becomes an issue. So some views are just hard. But we've had a lot of wins. In the last year, we've added some incredible good main extensions have been pushed out by the working group. Synchronization, validation's been at phase 2 now. There was enhancements to the multi-command buffer, multi-queue checking. There was a lot of SPIR-V runtime validation that was added in the last year. Performance is a critical thing that we care about. We know validation validation will reduce your performance greatly, and we are aware of that, and we don't want to make it so slow that it's unusable. So we do take performance checking. We have regression tests. And then lastly, we've added a lot more just generic GPU assisted validation performance improvements as well. So upcoming improvements, better error messages. Everyone should be happy about that. That's a priority of mine. Next is just, there's another engineer working on descriptor indexing. That's in the GPU assisted validation. And then also just better synchronization, timeless semaphore VUs. There's always more shader validation to improve. It seems like an endless battle. And again, we do appreciate all your issues that people raise. There's a lot of there's 18,000 VUs in the spec. It's very hard for us to monitor it all. So sometimes things slip. We do appreciate the community coming out and letting us know. With that, that is the end of my presentation. If there's any immediate questions, I can answer them really fast. Otherwise, I'll be around all day.
Good afternoon, everyone. Thank you for coming to my talk. My name is Ralph Potter. I'm Samsung's primary Khronos representative, where I devote the majority of my time and efforts to Vulkan. So since 2015, Samsung engineers have collaborated with both engine companies and AAA devs to enable some of the best mobile content. We've collaborated on around 50 major titles, including some high-profile releases like Call of Duty, League of Legends Wild Rift, and Diablo Immortal. That content spans a range of engines. About a quarter of those were custom in-house engines. UE4 is popular for high-end content on mobile. A few recent or upcoming titles on Unreal 5, and of course Unity is well represented as well. Today I'm going to talk about optimizations we have contributed to these titles and some related best practices that might be applicable to your own applications. So when we talk about optimizations for mobile, it's important to understand the environment we're working in. The primary thing that constrains us for mobile is heat. Your phone is a passively cooled device that has to remain comfortable to hold. And a lot of mobile workloads are bursty. Mobile SoCs are designed for those use cases. So you load a web page, you swap over to your instant messenger, you check the weather forecast. These are cases where we can schedule work on a relatively powerful CPU core. We can crank up the GPU frequency. We can boost the display refresh rate to 120 Hertz, so you get a nice smooth UI, and everything gets done quickly. And after that, we turn everything off and it all cools back down again. Games are not like that. So rendering workloads in games are typically more complex. The sustained CPU cost of game world simulation is often high. For 1440p displays are great for crisp text on web pages, probably overkill for games with rapid motion on screen. Ultimately, mobile devices can't maintain the peak frequencies that they're capable of indefinitely without generating excessive amounts of heat. And when that happens, we're forced to throttle back to something sustainable. Consequently, good optimization and squeezing as much performance as you can into a sustainable budget is the goal here. Even if your game can sustain 60 FPS, further reducing CPU or GPU overhead helps delay the point at which we throttle things. Vulkan brings us great control and a low CPU overhead driver, so this is an area in which Vulkan really excels. So a lot of what I'm going to talk about today is focused on memory bandwidth. Moving data around results in a huge portion of our energy consumption, and thus is a major generator of heat. And our ability to do this is not scaling with our ability to do more and more arithmetic. If there's one thing you take away from my talk today, it's that you should carefully consider what the memory bandwidth cost of an effect or a technique is, and whether it can be reduced to an acceptable cost. So I wanted to take a moment to talk about hardware rendering pipelines and what you might expect in mobile. So desktop GPUs typically follow a fairly simple conceptual model, at least. Maybe the hardware is quite a lot more complex, but the model is straightforward. We read vertex inputs from vertex buffers located in DRAM. And as soon as these inputs are run through the input assembler and the geometry processing stages, we can immediately push them to the rasterizer, start running fragment processing, and writing the results out to DRAM again. There's so much throughput and power in these systems that some inefficiency is acceptable. If we draw a triangle and then discover that another triangle was in front of it, we can just pay the bandwidth costs involved there. Immediate mode rendering is fairly rare on mobile. The new Samsung Eclipse GPU is an immediate mode renderer, but almost every other mobile GPU is some variant of a tile-based renderer, which is what we'll come to next. Tile-based renderers are a little different. So first, we're conceptually going to divide the screen into tiles and assign a geometry bin to each tile. Then we process all of the geometry at once and assign it to relevant bins as we go. This is different from the immediate case in that we need to have got everything done and back out to DRAM before we start on the fragment shading. Once we've finished processing all our geometry, we can then go tile by tile and perform our fragment processing. To aid in this, we typically have some small piece of fast dedicated memory that holds just the state of the tile we're working on. And once we're done processing that tile, we can look at whether it's actually changed versus what's in DRAM, write it out if it has changed, and move on to the next one. This has some implications. Writing transformed geometry back to DRAM makes geometry carry an increased bandwidth cost. So anything that generates large amounts of geometry is a potential source of performance issues. However, fragment operations become relatively cheaper. So clears and blending and multi-sampled AA can all be done entirely in the fast tile memory, so those bits become cheaper. So most of what your phone is doing day to day is UI rendering, and trading geometry throughput for fragment processing is exactly the sort of trade-off you'd want to make if what you care about is web page speed and home screen speed and the like, which is where most of your time on your phone is spent. So following on from that, some optimizations and best practices. The first one is going to seem fairly obvious, but it has some surprising niches to it. Only enable what you actually need. So enabling functionality in Vulkan is not necessarily free. The classic example of this, which we call out in the spec, is robustness, where ensuring that zero values get written for out-of-bounds accesses may require compilers to generate different shader code. A particular surprising case here, think about the extensions you need for your development build versus your production build. A consequence of enabling extensions that store shader properties, for example, pipeline executable properties or AMD shader info extensions, may actually be that the driver now has to retain different copies of your shaders internally, perhaps the copy of the intermediate representation or a disassembled binary. That's useful if you want information on screen in a development build, maybe statistics for diagnosis. It's probably less useful in a production build. This stuff might not impact your frame rate, but it will impact your memory usage. In particular, we recently reduced the memory usage of an unpublished high-profile title by 45% by disabling an extension that stored shader executable properties, simply because it was resulting in the driver storing disassembled binaries of every pipeline. So when we discussed tile-based GPUs, I described increased bandwidth cost for geometry. So this has some consequences. Essentially aim to avoid generating excessive amounts of tiny geometry. Keep your vertex structures small and think about how much precision you really need. Maybe your attributes, you can get away with 16 bits instead of 32. Typically, only vertex positions are required for the binning phase on tile-based GPUs. So splitting your position and the rest of your vertex attributes into 2 vertex buffers may well give you better cache behavior. Choose your image formats wisely. As I've already mentioned, memory bandwidth is a huge consumer of power and generator of heat. Smaller image formats will consume less bandwidth, less power, generate less heat. And in particular, I have an example from an older title and an older GPU, but nonetheless, this data from Forza, they had some pretty heavy kind of high-res beauty shots. And on older devices, switching from a 64-bit render target down to a 32-bit one delivered us some pretty sizable performance gains. So 7 FPS here and reduced GPU utilization. So again, reduced power usage. I will note that this is rendered at a fairly high resolution, which we'll end up talking about later. But for this particular use case, they wanted nice beauty shots. The high resolution was a deliberate choice by the artists. So render passes and subpasses are your route to getting the most out of tile-based GPUs. So I'm going to spend quite a bit of time on them. Before we dive into optimization, here's a quick conceptual model of how render passes work on a tile-based architecture. Essentially, your load ops will pull data from system DRAM, but your subpasses will operate on a copy that's kept on the small on-chip high-performance memory, and your store ops will write things back out to system DRAM. So the loads and stores to DRAM are relatively expensive, and the operations on subpasses comparatively cheap. So as the previous slide hinted, render pass boundaries result in load stores to DRAM. Those are costly. So in this example, pulled from a UE4 app, we have multiple render passes back to back, which could just be combined. So the translucency pass needs to read from the depth buffer, so it can't all be merged into a single subpass, but it can be merged into one render pass with 2 subpasses, and we still save a round trip through memory. So the table at the bottom here highlights the savings that we get from doing this. That's somewhere around 20% less power usage and consequently less heat generated. Continuing on redundant work, empty render passes. This sounds really simple, but we see this happen quite a lot in practice, particularly because of how API abstraction layers in engines are implemented and kind of lack of information about what's going to happen after they've opened a render pass. But setting up render passes is not necessarily free. Which may still involve mapping out where various resources are going to sit. So we tend to recommend deferring actually calling CMD begin render pass until your first draw if you can. Essentially, if possible, drop anything that contains no clears and no draws. On the subject of clears, Vulkan has 3 ways to clear images and attachments. And to ensure that things are done efficiently, it's important to choose the right one. Render pass load clear ops are essentially free on most tile-based architectures, and so that should be your default choice for clears if you can do it. CMD clear attachments within a render pass should still be relatively cheap. You're writing to the on-chip memory, Whereas clearing color images and clearing depth stencil from outside of a render pass, unless you have no choice, it's likely to be the least efficient option. I will note that I said earlier, not all mobile GPUs are tilers. The Eclipse GPU is not, it's an IMR. But we still find that if you follow this guidance, it's no worse on the IMR than it would have been. So just follow the tiler guidance, you'll be okay. Kind of pulling some things from the last couple of slides together, you can't trivially drop a render pass if it contains clears, even if there are no draws, but you might be able to push those clears down into a subsequent non-empty render pass with a bit of cleverness. So we tend to recommend building a list of pending clears and flushing it before the first real non-empty render pass. If you're really lucky, you can actually propagate them down into the load ops of subsequent render passes. On the subject of load ops, choose them carefully. Use load ops don't care if you by default, but it does mean that the contents of the attachment are undefined. Use load op clear if you need something to be cleared to a known value, and load op load if you really do need previous content to be preserved and copied across. Load op none is a special case for where you don't need to access the contents of the attachment, but you need it to be preserved for later. In this case, you can't just use don't care because things potentially get invalidated. If attachment images are never loaded or stored, allocate with the transient attachment image usage and back it with lazily allocated memory. So subpasses and load ops again. So this is another one from UE4. This is a bunch of post-processing passes, each of which is drawing a single triangle covering the entire viewport. And we happen to know in this particular case that we don't need to clear because every pixel of the output is going to be written to. That might not be true in every general case, but here we know it's true. And so we're swapping from clears to don't cares. Similarly, we get to drop some load op loads because we know we're accessing inputs to these passes from samplers and not from render pass attachments. Store ops at the end of your render pass also matter. Store op store carries the highest cost, but if you need the rendering you've just performed to actually be written out to memory, then this is an unavoidable cost. The only caveat here is do be careful about not storing things that you no longer need. If you don't need it, use don't care and let us throw it away in the driver. So what about dynamic rendering? Recently, Khronos released the dynamic rendering extension and subsequently promoted it to crawl. It's a great improvement in terms of usability. Developers that I've spoken to really like it, and I occasionally get asked about the performance, so I wanted to address that one. By default, the extension only supports a single subpass per render pass. For that use case, the performance is equivalent to traditional render passes. Khronos also recently released an ext shader tile image extension, which provides equivalent functionality to subpasses. It's a little different, but it gets you back to the same place. This brings us up to the point where dynamic rendering is more usable than render passes while still addressing the same problems and with comparable performance. But that does leave one final issue, which is adoption in the marketplace. Dynamic rendering is available on the latest devices, but it'll be a few years before it's got availability that most commercial developers will want to see. So I would say if you're doing something experimental, go for it. If you're trying to ship a commercial app, maybe you need to wait a while, but we're not concerned about the actual performance of it. Eventually, we will be recommending that you use it. Okay, so now on to upscaling and how and when to apply it. So a common bottleneck we see is fragment shading execution time. So to reduce per fragment shading cost, game scenes can be rendered at a reduced resolution and then upscaled before rendering the user interface. One caveat, there is a bandwidth cost to upscaling. So if your bandwidth limited rather than shader fragment limited, this may not help. Only apply this when it will. Upscaling can be performed multiple ways. You can do it with a blit. You can do it with a full screen textured quad. You can do it with compute shaders. CMD blit image might seem like the best option. it tends to be less efficient than actually just rendering a full screen textured quad on mobile GPUs. This is to do with requiring you to break render passes and have explicit copies. Recently, kind of more complex super resolution techniques have started to become popular. AMD's Fidelity FX library, for example, is implemented as compute shaders. That provides good results on both the Eclipse and Qualcomm GPUs. I can't comment about the other mobile vendors. We haven't tested them, but the results we've seen from it are very good. So this slide illustrates the effect of using Fidelity FX's edge sharpening filter as part of an upscale. This is a small fragment of the frame blown up significantly. It's probably hard to see on the projector, but the highlighted slide on the or section on the right should show you the differences. Essentially, you're going to get more defined edges, and the details should be more legible. So I'll just leave this up for a few seconds. Okay, so the graphs here come from Nightcrows, which is a recently launched UE5 Korean MMO. What we have here is FPS for OpenGL in purple at around 51 FPS, Vulkan in orange, including some Samsung optimizations to the base engine at 57, and then Vulkan upscaled with edge sharpening at a solid 60 and with reduced GPU utilization. I believe this is an S23 Adreno. I'll also note that these numbers come from a device where the frequencies were locked to a sustainable level. So you'll likely see higher numbers on an unlocked handset, but nonetheless, we get a solid increase from upscaling. And you can also see a really solid gap between what we would get from GLES and what we get out of Vulkan. Okay, getting close to the end, but I want to talk about swap chains and presentation for a moment. So a few best practices on presentation. First of all, unless you have a really good reason, and I mean like I'm writing a VR compositor level of good reason, prefer the FIFO present mode over Mailbox. Generating images and then throwing them away, as Mailbox is prone to do, is not good for our goal of reducing energy usage. Set your min image count for swap chains to 3. Be prepared for the fact that you may well get more than that back. And finally, we tend to recommend using a separate thread for presentation. It's not particularly obvious from the spec, but QPresent is allowed to block, and on Android it will do so. It can do so for multiple reasons. Some of it's the loader in Android, some of it's drivers. Sometimes it's just the application getting too far ahead of the GPU. Regardless of that, it's simpler to move the presentation to a separate thread than it is to handle the unexpected waits that come and consume a whole chunk of time on your main thread where you're probably also trying to run your simulation. Swap chain pre-rotation. So when your user rotates their handset, the relative orientation of the display and the render surface change, and somebody has to be responsible for making sure that everything gets fixed back up and that we don't get weirdly squashed and scaled images on screen. So either the application can do that work or the operating system compositor and the display hardware can do it. For some devices, they have display processors that will just do this almost for free, but that's not the case for all handsets or in all situations. If the operating system compositor does it, it has to read your application rendered image, apply a 2D rotation on the GPU, write it back out. That's costing GPU time, it's costing bandwidth, and it's costing energy. So in the screenshots I have here, you'll see the same image, but actually the resolutions are different. The X and Y resolutions are flipped. That's because the image on the left was actually rendered vertically and then rotated by the OS compositor, while the one on the right was rendered in the correct orientation and gets to save some work. So what happens if we just leave this to the Android OS? Well, the handset may contain a display processor that can do some amount of composition basically for free, but it might not. And in the example I'm showing here, the device doesn't. So if you trace through a particular color, say the blue one, you can see where where it's waiting on the application, where it's waiting on the GPU, and then how long composition takes. And in the lower case, where the GPU compositor is doing the work, composition takes way longer. So if we're letting the OS do it, yeah, you'll get the right output, but it's costing you power and it's costing you time, and it will preempt you. And the compositor has a higher priority than you. It will preempt you and steal the time for you. So worst case, we're talking about something on the order of 2 milliseconds a frame if you don't do the pre-rotation yourself in the app. So we recommend you handle pre-rotation yourself if you can. Android has a great article on how to do this. If you can't do it yourself in the app because information isn't available in the right place, Qualcomm have a handy extension for you that does simplify this, but it's not available on all devices. But for the devices where it is, if you don't have any other choice, it's better than doing nothing. So some takeaways: mobile optimization is not just about frame rates, and reducing the work required by your application will reduce the risk of us throttling you. And finally, kind of understanding the GPU architecture, particularly around render passes and memory load stores, will help you a lot. Think about the bandwidth costs of what you're doing. That will get you a long way forwards. And as a final thought, profile your issues, don't guess. If you optimize for something that is not the real bottleneck, you're not going to get anywhere. And on that note, thank you.
Welcome back, everybody. So let's begin. This talk is going to be an introduction to SPIR-V. 今回も日本語バージョンのサイドでご覧していただきます。Okay, so yes, this is introduction using SPIR-V. I know you guys are all excited to hear about SPIR-V. Who am I? I'm Spencer Fricky. I work for LunarG. I've been working on SPIR-V now for about 3 years. Just a little heads up, I've only done the Vulkan part of SPIR-V. I'm not an OpenCL expert. I'm also not a compiler engineer by trade. I've learned a lot about compilers from my time working with SPIR-V. And I have been part of the SPIR-V working group in the past, but I was not there when it was created, so I can't answer any questions of why SPIR-V does things that it does. And so the question is, who's this talk for? And I would argue anybody who's ever had to open up a SPIR-V disassembled file and just look at it. I got into SPIR-V 3 years ago because I had a simple task of checking at runtime how many loads and stores instructions there were. And I went to Google how to parse a SPIR-V file and found nothing. And so this is hopefully a talk for anybody who wants to just learn the basics of, doesn't have to be a tool, but just a simple script to work with a SPIR-V. So what is SPIR-V? There is a proper definition of its interchangeable format. But when I explain SPIR-V to people, I first start with a CPU. So the CPU, you have code, and you compile it to your correct ISA that you're going to run on the various CPUs out there. And GPUs are the same, and most people understand that as well. You have your GLSL, HLSL, you compile it, and you get off to your vendor, and they'll bring it down to their GPU's ISA. And with the CPU world, there's this beautiful LLVM ecosystem that has become very popular, where you take your front-end language, you bring it down to LLVM IR, where you can have all these toolings, optimizations, and ultimately get it back out to whatever assembly you're aiming for with the back end. This is what SPIR-V is, but with GPUs. You can take your front-end language, such as popular ones, GLSL, HLSL, and once you get to SPIR-V, we can run SPIR-V optimization on it. There's a lot of tooling that goes around this intermediate representation. And then when you're done, you hand it off to your GPU. The compiler and your driver will then take it and turn it into its ISA. And what's beautiful about SPIR-V is that in OpenGL, you had to do all this front part up at runtime. So you would hand OpenGL, you would have to hand them the GLSL, and all this would have to be done. Now we do it offline before we actually execute the program, which gives an incredible performance advantage. So SPIR-V is very heavily inspired by LLVM. LLVM IR is slightly different because it is a CPU-based IR, and it's just the internal details of the LLVM project. SPIR-V is a proper working group spec by the Khronos group. Multiple companies come in, and we have extensions and new features all GPU related. There is a tool for bidirectional translation between SPIR-V and LLVM. I have not used this tool personally, but I've been told it works very well. So there's a SPIR-V dialect of LLVM that can be translated between the two. When working with SPIR-V, you'll go on the SPIR-V spec and you're going to see the words shader and kernel. What this really is just a way to tell people in the spec that the SPIR-V you're looking at is only for OpenCL or Vulkan. For example, there's no fragment shader concept in OpenCL. OpenCL doesn't have a fragment shader, so it'll be labeled as shader. And there's certain things that Vulkan does not support, which will be labeled as kernel. Also, like something that people don't realize is that there's two different memory models. There's a logical and a physical. Physical is what you can think of as a pointer. You have a linked list and you want to bounce around. That's a physical pointer memory model. Vulkan has by default a logical memory model, which is a set of access chains. And but there are physical memory models, but they're behind extensions and are some limitations to it. Next is the SPIR-V grammar file. So all SPIR-V is based off this JSON file and the SPIR-V headers, the path you can see at the bottom. It's equivalent to the Vulkan's VK XML. All the instructions in the spec are generated from this. And so yes, that's kind of the heart of what SPIR-V is, where it's listed. You can use this for code generation. Be careful how much you use it with. But for us at the validation layers, we took this as an opportunity to, if in case someone added a new image operand, we were able to easily parse this file and create a function that detected how many operands there were. So next, we're talking about SPIR-V extensions capabilities. SPIR-V is a IR. To use it, you have to have a client API, such as Vulkan or OpenCL. And there's this idea of you want to add features to SPIR-V, but you need a way to communicate that these features are being used. And that's what capabilities are. Capabilities are the term in SPIR-V that you can kind of translate to a Vulkan feature bit. And as an example, I have this JLCL shader. What it does is not important, but when you compile it, you get in the bottom, you'll get the OP capability, uniform and storage buffer 8-bit access. So that means this SPIR-V shader is using that feature, that capability. And this is great, but your GPU might not support it. This is a valid SPIR-V. The SPIR-V validator will not yell at you. But when you run it, if your Vulkan implementation does not support that feature bit, your GPU can't support it. And so luckily, I want to say about 95% of capabilities and Vulkan feature bits are the same, like exact spelling, minus the first letter is not capitalized. So it's actually very easy to find. But so the capability system is a way to map it up to the client API if what features are being used. So then in this case, the validation layers can check to make sure you're not accidentally using something that your driver's compiler won't understand. Next, let's talk about SPIR-V instructions, because SPIR-V is just a stream of instructions. That's all they are. It is. So all these instructions have opcodes. They're always with the prefix OP. And then there's the operands, which are just the 32-bit words that follow the opcode with all the information about it. Before we get into this, I just want to clarify, SPIR-V is a binary format, but everything you see on the right over here, that's the disassembled version. So in the presentation, we're always going to be looking at disassembled SPIR-V. But if you have to break down into a binary, what does it look like? So here's an instruction, OP type int, and this is the binary for it. And so that, look at the binary, it's kind of scary, don't know what it means, but the spec, if you look at the spec and the bottom row, the spec is always broken into two parts. The first part explains the instruction. This bottom mythical row actually has all the information about the binary information. So the first instruction in SPIR-V is split up. The first 16 bits tell you how long the instruction is. The next 16 bits tell you which opcode it is. In this case, it points to the OP type int. Then you have the result ID, which in this case is just UN32 pointing to the value to ID 6. And then we have two more int32s pointing to the values for the width and if it's signed or unsigned. And then we put it all together, that's in a single instruction. It's just the binary, but in binary representation. Something to be careful of is this catches me off guard. when I first started is disassembled SPIR-V likes to flip the result type and the result ID because it's just easier to read. But when you're parsing it as a binary, you have to remember the spec is the answer, just like Vulkan. The spec has all the answers, so you always go left to right when you're parsing it from the spec. So how is SPIR-V laid out? Like I said before, it's just a stream of instructions that are all 32-bit words. The first 5 are the header. We have a magic number, the SPIR-V version that you're using. Some generators like GL Slang will inject what a generator is from, so you can know that. And then how many IDs are being used. And the rest of it is the instructions. It's a very, very simple file format, actually. Inside the main SPIR-V, there is 5 sections. And each section has some dedicated instructions that are allowed. Don't worry, SPIR-V val will tell you if you're wrong. The first one is the mode setting. So this is the very high level information, such as the entry points, what capabilities you're going to enable, declare. If you're using a fragment shader, this is where you could set the execution mode, if it's upper left or lower left. This is all defined at the start. Next is the debug information. Every tooling makes use of this section. This is where you put things such as the variable names, the source it came from, anything you can think of debug-wise will be in this part of the SPIR-V. And then the annotations. Mostly these will be declarations. So if you have variables ahead, you can decorate them with things such as non-writable, non-readable. All this annotation stuff happens next. Then fourth is the types, the variables and the constants. We'll get into types in a bit, so I'm just going to leave it at that. But if you have interface variables, such as your input-output variables, descriptors, this all gets defined as variables at this part of the section. And then lastly, you have your constants or specialized constants are also going to be declared here. And then last and most important are your function blocks. So this is where the actual logic occurs. Your loads, your stores, your calculations, sampling, all this happens in the function blocks. So the blocks are a 2-part thing. There is the same thing as LLVM. There's a function block, and inside of that, there's blocks. That's how it's described in the spec. And to give an example, on the left, I have some GLSL code. It's very simple. There's an add instruction, and then inside the main, we run the add function, take the value, and then check if it's less or equal to less, if it's greater than 0, and do a conditional from there. On the right, I'm using the SPIR-V visualizer tool. There's the 2 red blocks are the function blocks. So breaking this down, let's take the add function. So this is what it is. There's about 9 instructions. The first instruction is always defining the function. So this is how you know where the function starts. And with every start, there has to be a place where the function ends. So this is how we know where a function is inside a SPIR-V module. And then there's these blocks, and every block will always start with a label, OP label. That's how you know a block starts. And then there's various ways to terminate a block. In this case, we're just going to return the value. But so as you can see, all these blocks always are bound by an instruction and a termination instruction. So breaking out to our main function, the first thing you're going to notice is there is where we actually make the function call. So this is where we would have made the function call, go into the other function block, and now we return. And then after that, you have we have to declare, before you do any control flow, you have to declare it. So you have to tell it, hey, we're about to start a control flow. And if you see the value 38, that's just pointing to where the control flow merges. So if you ever diverge, you have to know where you're going to reconverge. And if you haven't figured out, the whole idea of these blocks is it makes all the control flow analysis much easier because you know where everything's going to reconverge. And then we actually do the conditional. So in this case, it's going to be a branch conditional. We're going to take the value of 36, which will be wherever C greater than 0 evaluates to. And then there's going to be 2 potential options. Both of them are going to be blocks. So it's going to either go to the first label or the second label. And then every block has to terminate. There is no idea of falling through. Like there's no switch case fall through style. Every block will terminate. In this case, they're both going to go to the reconversion block. So how do you parse a SPIR-V file? This is all you need. It's actually incredibly easy to parse a SPIR-V file. First thing you do is you just offset 5 bytes if you don't care about the header. Otherwise, you just go off 5 bytes. And then you just have a SPIR-V module. You jump into it at that offset and grab the first instruction. From there, you get the length, which was the first 16 bits. And then you can increase the offset, and that will get you to the next instruction. And then next thing you're going to want is the opcode. And from here, you'd most likely have a switch statement, which would, depending on what opcode it is, do whatever operation you need. So with that, that's all it takes to parse a SPIR-V file. And I wish I would have known that 3 years ago. So next is the extended instruction sets. This is something that caught me off guard. So the best way to explain this is SPIR-V is agnostic, and certain things like trigonometry functions, such as sine, cosine, have much different accuracies depending on which front-end language you're using. And so to get around this, so in this case, you have GLSL. I'll do it by example. So GLSL, we have a sine operation. If you do this in GLSL, you'll be importing the GLSL STD 450 extended instruction set. That's a mouthful. And so this is what the spec looks like. It just shows it's a sine instruction, and then in the SPIR-V, what it looks like is this magical OP extension instruction import. That just tells your module that you're going to be using this extended instruction. And then we just want to use the sine instruction. So if you look at the binary value of that, it's the value 13, which references in the spec. So yes, this is how extended instructions work in SPIR-V. It's complicated, not too complicated. It's just an extra indirect hurdle that you have to be aware of. Next, entry points, execution model, and execution mode. So when someone talks about a SPIR-V module, that's really just a file. You can actually have multiple entry points, like a vertex and a fragment shader entry point in the same module. And then I just want to mention model and mode are usually the biggest two typos I always mix up. So be careful when typing it. So going to entry points, here's a hypothetical shader language, which has a vertex and a fragment entry point, and they both use the same common helper function. If you look at the SPIR-V, what you'll notice is that there's 2 entry points, and they both have an execution model, which in this case is a fragment and vertex, and they both point to the function that they'll start in. Next is the execution mode. So in this case, we have rounding mode, round to even and round to 0. So we can actually have 2 different execution modes on the 2 different execution models. And so this is something that you can take advantage of. With types, so the whole execution model mode, most people might not ever touch, but it's something to be aware of if you have to. But moving on to types. So types are great. Types are a way to define any type in SPIR-V. And you can use smaller ones to build bigger ones. And once you define them once at the top of your SPIR-V module and use them across the function blocks. So let's say I want to make a matrix 3 by 2. That's the same. What that is 3 vector 2s. So what you do in SPIR-V is you create a float. So in this case, OP type float, we say it's 32 bits wide. And then we use that float to create a vec2, which is just 2 floats and a vector. From there, you use that to create a matrix of 3 columns wide. And with that, we have now successfully created a 3 by 2 matrix type, which can be used now across the module. Structs, same thing. You have your int. In this case, we're going to declare the int and the float that we're going to be using here. And then the struct just lists them out. So it just lists out in the order of the struct all the types. As you can imagine, these types get crazy when you start having arrays of structs, structs of arrays, but they're all built off of smaller types. So lastly, we're going to talk about access chains. This is something I want to self-admit. It took me about maybe a year or 2 to finally realize that access chains are just a chain of accesses. You think that'd be obvious, but it's easier now. Maybe I'll show you an example. I'll show you an example of what they actually do. So I have a struct here. It's a SSBO buffer, and I want to access part of it to store a value. So so right there, I want to make that access so I can store the value. And this is what the access chain looks like. And this is where the confusion starts, but it's not that bad. So the first thing is the result type. So we're going to be storing a float to it. So the result type is just a 32-bit float. The base object is the struct. So that's simple. We point to the struct, which is the base variable. And then these last three are just indexes, which in this case, we know at compile time, these are not dynamic. So they're just constants. So if you turn those into constants, you get the values 1, 2, 2. So trying this one more time, we have the struct that's the ID 13, and we're going to index into one of the struct, which in this case is the variable B. And then we're going to index into the second part of the array. And then after that, we're going to access into the second component of the vector, which will be the Z component. And so with all that, we tell it where in that variable we want to access, and then we store the value. So it's quite literally a chain of accesses, but yes, it's a and that right there is the logical memory model that I was talking about earlier. So yes, with that, I was trying to catch up some time for us. That's about as much SPIR-V as most people want to hear in a day. Is there any questions about SPIR-V? We have a few minutes. Okay. This is the final talk of Vulkan, to my knowledge, for the day. So yes, this talk is going to be the Vulkan ecosystem developer tools. By now, you should know I'm Spencer Fricke. I work for LunarG, and I'm way too stacked about the Vulkan API. I have been working on Vulkan since it came out as a college student, and then as a hardware vendor, and then independently, and now I work with LunarG. I have seen the ecosystem grow in the 7 years. There's been a lot of tools, and the best way to describe it is you're not going to use them all, but it's very important that you are aware of them. I guess my goal of this talk is if one person learns about a tool and uses it next week because they didn't know about it, that's a success. I'm not going to be able to talk about every tool, and this is more of, and I've not used them all personally. I feel I have enough information about them to warrant talking about them. So quick recap. A lot of these tools are affecting one of these 4 blocks, either the application, the loader, the layer, or the GPU. So it's important to understand what a tool is doing and which one of these it's going to affect. Also, the concept of offline and online. So some tools are designed to be done before execution, while some tools are designed to be done while you're executing your program. So this is also an important distinction to know. Next I'm going to tell you is to grab the SDK. The SDK is great. It has a lot of these tools ready to go, built for you, tested. Throughout the presentation, there'll be a little SDK sticker to indicate that they are in the SDK. And all this information is off the latest version of the SDK. So the first one, which is kind of a tool, is the Vulkan headers. It's the base for every tool, every application. Everyone needs the Vulkan headers. These are C headers, C99 headers provided by Khronos. They define all the structs, the functions, and every time there's a new spec update, there'll be a new header update. But for the people who are C++ purists, we also provide a Vulkan HPP header. So this is just a C++ version of the Vulkan header. But if you're on Team Rust or on Team JavaScript or wherever, luckily the community has got you covered. There's many bindings for every language. The community supports this. But yeah, so hopefully you can use Vulkan in whatever environment you're most comfortable with. Next is the Vulkan loader. So the loader is that part of the block. It's the interfaces between your app and the rest of the layers and GPUs. Khronos provides a Vulkan loader implementation on the GitHub. It's built into the SDK. If you're on Windows, it will actually come with your driver. And it is a reference loader because on Android, they have their own loader, but the loader is just a small, thin library that is used to bind your app to everything else. Next is the Vulkan validation layers. I gave a talk about this already. I'm going to say this is unbiasedly going to say this is the most important tool you need, and you should have it enabled at the start of your application and have it set up. First thing you do is set it up. It's for development, and will catch all your errors and everything you would ever. Next is API dump. This is a nifty little layer. It's all generated. It's simple. It just prints out everything, which can be incredibly useful when you want to guarantee what you actually sent down to your GPU or for a bug report. you can dump out everything. And it can get very large. So this is a screenshot of an API dump. It lists 2 functions, and as you can see, it pretty prints everything. And you can also see Vulkan gets very, very verbose, as it has a lot of stuff in just 2 functions. But luckily, we have this layer is configurable. So there's a lot of things you can do to help reduce the size and print out what you actually care about. Next, we're going to talk about the tool GFX Reconstruct. There was an old tool called VK Trace VK Replay. This is a successor of that. This tool's main objective is to capture and replay traces. It's cross-platform, and it's now, as recently, API agnostic with a DX12 compatible use of it. And so you hear the term capturing and replaying and tracing, but sometimes that doesn't make sense to people who aren't used to this. So what tracing is when you have an app and you want to run on the GPU, you can have a tracing layer. This layer is going to capture all the functions, all the data, everything you send to the GPU. It's going to take it and write it out to a file. And then that's a trace. The .gfxr file is the trace. You have now captured it, and now you can replay it. So GFX has a replay tool, which is just basically an application. It's an application that reads this file and plays it back. And what's beautiful about this is every time you play the app with the same file, it will produce the same thing. And this is where the use case of GFX Reconstruct becomes very powerful. You have essentially eliminated the app as a debug vector. And so now when you every time you want to run something, it's going to be the same. And so hardware vendors like this because they can just have the same input every time. And if you're doing a GPU architecture simulation, you usually get to look at one frame because it takes so long. So this is another tool that's designed to help capture things, reduces the frame that people care about, and you can replay that single frame. And it's also just great for debug reporting. If you have a bug and you don't want to share the source of your application or just have someone have to build your application, you can give a .gfxr file over and people can just replay it if they have the same device. And even if they have a slightly similar device. So GFX Reconstruct has a lot of tooling around it. It's all in these nice Python scripts. The first one is the optimize. So as I talked before, sometimes you trim your trace and now it's only one frame. But if you look at it, you've created a bunch of images and buffers and pipelines that are not going to be used in that one frame. So optimize can go through offline and reduce that to help greatly reduce the size of a trace. All these files are compressed, the GFXR files, and so we have a tool to help with the compression, decompression of it, change what compression format you're using. If you're interested in grabbing the binaries of the SPIR-V binaries, if you want to grab the SPIR-V binaries out, you can also use the extract tool to grab that up. And then lastly, if you just want to see what your GFXR file is, there's a nice little info tool to give you a summary of that binary file. Lastly, about GFX Reconstruct is the convert tool. This is a really powerful tool because it essentially is API dump, but you don't have to run the app anymore. So it's great for debugging, great for reporting issues, because you've taken the file that you already traced and you can just get all the information out of it in a nice parsable JSON format. So it's a very useful tool of the GFX Reconstruct ecosystem. So next, we're gonna talk about the extension layers. So this is a repo that has been slowly growing. And the idea of this is to implement a layer. So if your driver does not support it, we can still run it on any device. Designed to be shipped with the application. Every one of these has a different story. So via the timeline semaphores, that was added because older operating systems, the kernels could not support timeline semaphores. So we produced a layer so we could guarantee that people running on old OSs could still use this feature in Vulkan. Synchronization 2, that was an API redesign. So we wanted to just make synchronization slightly easier. And so we redesigned the API, but we wanted a way for people to truly use it and not have to worry about driver support. So this layer will emulate any synchronization 2 back to the core 1.0 synchronization primitives if your hardware does not support it or your driver doesn't support it. And then lastly are these 2 new ones that came out recently, EXT shader object and NV memory decompression. These are just 2 ways so people can start developing on with these extensions regardless of what they're running on. So the Vulkan profiles. So there's a lot of background behind the profiles I do not have time to go into, but the profiles are basically a way to describe what's on a device, all the queryable information. And this repo has the tooling around it. So because profiles is at the base a JSON schema, which is defined in this repo. But there's also a layer. The layer is used to emulate any of these profiles. So when I say profiles, maybe an example would be better. So when you query your GPU, the first thing you get are all the extensions. And then you get what features are on it. All the formats have various format features to them. And then lastly, you have all these limits. So all this is defined in a Vulkan profile, which then has all the tooling around it. A use case of this is actually the validation layers. We use this for testing. It's fantastic. If a new extension comes out, most likely none of us will have hardware to test it on, but we still want to run validation. Luckily, when you're writing a layer, you don't sometimes need to worry about what actually gets sent to the GPU. So we just have the profile layer used so we can trick it into thinking that we actually support these extensions and have these various features enabled. And then we use it with the mock ICD driver so we can make sure everything works, which brings up the question, what's a mock ICD driver? So this is a null driver, mostly generated, a lot of exception functions. The whole idea of this is it's great if you don't care about the GPU actually rendering something. So layer developers is very useful. If you just want to test your layer and not what actually happens after a layer, this is a nice little thing you can grab from the Vulkan tools repo and build quite easily. And going back to the idea of profiles, there is the Vulkan info and Vulkan cap viewer. So these are 2 tools that also display information. Vulkan info is the command line tool, and Vulkan caps viewer is the GUI tool that has a database with it. So first off is Vulkan info. Vulkan info is just a simple command line. This will print out everything on your GPU. Some of you might have used this. There's a -- summary if you want the less verbose version. So this is just gives you a quick overview of what's on your device. Vulkan Cap Viewer is a beautiful UI tool that will display everything for you in a much easier fashion. And then in the top, in the middle, you see the database. So you can submit things up to the database. And so thanks to Sasha Williams, who created and maintains this website, there are now many Vulkan implementations that have been reported on various devices, and it shows all the features, extensions, and it's just a great part of the ecosystem. And the best part is any one of these you can grab and get a Vulkan profile from them. So the whole ecosystem has kind of come together to use these Vulkan profile JSON schemas to help represent what's on a GPU. Next, Vulkan configurator. So if you ever use multiple layers, you'll find that, and you have to configure the layers with all the settings, you find it can be very difficult. And this is where Vulkan VK config comes in. It makes just using layers easier. It's a UI tool, and this is what it looks like. So you bring it up. The first thing you'll see is on the right is where you have all the settings. So if you came to the validation layer talk, you would have saw all the different settings. This is where you can set them all. On the side over here, in the middle is where you set which layers you want to use. If you use layers, the order matters. That's a very common mistake. So this is a great way to just make sure you have the right order of what layers you want. And then lastly, you have the way to launch your application and to use the layers. Next is VK Cube. I think this is the most underrated tool there is. I use it all the time. When you start messing around with your loader, your driver, your layers, sometimes you have to just make sure everything's still working. And it does a simple texture draw. It runs WSI. This is my favorite tool. It's 6 characters in your command line. Highly recommend it. Next is okay, so next part of this is just gonna be a lot of shader stuff. So there's a lot of shader tooling in the ecosystem, and sometimes it can be overwhelming, but so we're gonna break it down little by little. First is GL slang. If you've ever used GLSL, most likely you know what GL slang is, because that's the Khronos reference compiler to bring GLSL down to SPIR-V. There's also basic HLSL shader module 5 support, but yes, this is a tool there's both standalone tool that you can use offline, and it also has a way to use it as a library for online usage. Next is DXC. DXC is Microsoft's tooling to go from HLSL to DirectX, but there's actually a SPIR-V backend. So we can use DXC to take your HLSL down out to SPIR-V, which then can be used in your Vulkan runtime. Next is CL SPIR-V. People like this. So the whole point of this is to take your CL kernels to SPIR-V compatible, Vulkan compatible SPIR-V. Adobe has showed like they took millions of lines of code and OpenCL kernels, used this tool, and were able to run on Vulkan runtime. So this tool does work. There's a lot of workarounds. They're all well documented there, and it kind of shows you the difference of parity, feature parity between Vulkan and OpenCL. Next is SPIR-V tools. So this is a collection of tools maintained by Khronos to kind of facilitate all the basic needs of using SPIR-V. The first two are the assembler and disassembler. So if you want to go between binary and disassembly, this is the two commands you're going to be using. If you need to optimize, there's a SPIR-V opt command. So this will optimize the SPIR-V for you. If you run this and type in --help, it will list all the optimizations with a description. So if it's designed to run offline. And yes, so this is a tool that will do all the optimizations for you on SPIR-V. Next is a great tool, SPIR-V diff, which a great use case if you do an optimization and you want to see what it did, or if you do two different optimizations, you want to see the difference. This is a great tool to see what is actually the difference between two SPIR-V modules. There's SPIR-V reduce, which will take a SPIR-V file and attempt to simplify it to try to reduce your bug, try to reduce the bug to the most simplest possible SPIR-V. And then there's SPIR-V fuzz, which has been used a lot in the CTS testing. It takes a SPIR-V, applies all these semantic preserving transformations to try to really, make sure things like the drivers are being able to handle these variations of SPIR-V. Next is SPIR-V cross. This is a separate repo, and the idea behind this one is to take the SPIR-V and bring it to a human readable language. The most common use cases is you have a SPIR-V file, you have no idea what it does. Most likely you wanted to just bring it out to GLSL, HLSL to get an idea what it does. That's what this tool can do for you. But another, to my knowledge, still, this has been used for portability. So you can take a SPIR-V for something aimed for Vulkan, bring it back out to Metal MSL, and be able to use it on Metal as well. So this tool can be used for portability as well. Next is SPIR-V Reflect. This is a runtime library designed to help you parse the SPIR-V file, because parsing a SPIR-V file is not fun. So this is a simple header. You add it in, and it can give you information such as descriptor locations, any interface variables, anything you might need at runtime decisions. So this is a little code example from the GitHub. The first thing that you do is you just hand in your module, create a SPIR Reflect object, and then it has a very Vulkan style way of enumerating. So you get, and once you get the, in this case, the input variables, you can get the information about them, and then be on your way in your code to do what you need. So last SPIR-V one is the SPIR-V Visualizer. So this is a web UI tool. It's a front-end tool. We host it on Khronos' website. If you ever have to look at SPIR-V, I highly recommend using this over SPIR-V disassembler, because it at least gives you a nice visual idea and makes it a little bit more digestible to understand a 10,000 line SPIR-V file. Next is Amber. Amber is a cool little tool. Sometimes you have a SPIR-V, a problem with the SPIR-V module, and you want to just run it, you want to test it, but to do so, you need to create a Vulkan pipeline layout, a descriptor sets. You have to create all this stuff just for the sake of testing a simple shader. So Amber's goal is to try to reduce that overhead. So this is what an Amber file looks like. So as you see the top, this is where you would put your either, it supports everything, supports GLSL, HLSL, SPIR-V disassembly. So you put your shader there, and then you do things such as allocating your buffer, creating the pipeline where you attach those shaders, setting your location of any interface. And in this case, you can do, I do a clear, but they also have things for drawing, dispatching, and then they also have the ability to do pixel checking, so, or buffer checking, so you can actually have this be as a unit test as well. Next is RenderDoc. I'm gonna assume most people by now know what RenderDoc is. If you don't, I highly recommend looking into it. It's a popular debugging tool that works on basically you give it your application and every frame it will give you all the information you'd ever want. It's fantastic. People use it all over the industry to debug random artifacts and issues with their graphical programs. As of lately, so Greg Fisher, a few months ago at 2023 Vulkanize gave a great talk about shader level debugging. So now inside RenderDoc, you have the ability to debug from your source level shader, which is an incredible addition to what was already a powerful tool. Next, I'm just gonna make a blanket statement and say if you're on a hardware or platform, you should probably look into their tools. Most vendors and platforms have their own tooling that's designed to be the best it can be on that particular hardware or platform. So if you're on so don't be afraid to look at your platform or hardware's tooling set. Next, I'm gonna talk about Swift Shader and LavaPipe. So these are two open source CPU implementations of Vulkan. So the idea, so Swift Shader was created by Google, LavaPipe is created by Mesa. They're great for just trying to eliminate as a reference. It's not a reference driver, but you can use it as sometimes I do it where I think there's an issue with my driver. I can quick run on 2 extra implementations and just get a good idea if where the bug might be. So these are very, and they're all both open source. You can grab and build yourself. Fantastic. Next, I'm going to quickly just talk about CTS. Most people don't ever have to worry about CTS, but I think it's important to be aware of it. CTS is the many tests that have to be ran in order for implementation to be Vulkan compliant. So any Vulkan driver out there that's compliant has passed all these tests. So if you ever are looking for a set of millions of positive tests for Vulkan, this is where it is. Next is Vulk. Vulk is a nifty little header library. It's a meta loader, and the idea of it is to help reduce your function overhead for every function you call in Vulkan. To do this, you have to be doing indirectly linking of the loader. So when you're directly linking, that means at compile time, you have already took the loader, linked against it, and you know where the functions are. But at indirectly linking, that's a runtime thing. So at runtime, you grab the loader and you do a DL SYM or DL open to get the functions, and that's when you can use Vulk. So this is what it normally looks like. You have a application, and there's a special VK get device proc address function where you pass it the string of the function you want, and it's going to go get the function pointer. So you go down to the driver, you get the function pointer so you know where to call, and you hand it back. So without Vulk, you normally would just call the function again, and it would do the trampolining through the loader down to the GPU. The idea behind Vulk is the second time you don't need you know where it is. And so Vulk is just the nifty code that you would have to write anyway to just bypass this. So now when you use Vulk, every function call can save that extra function jump, which can add up, every little bit of performance can help. Next is VMA, the Vulkan Memory Allocator. So this is a very widely used tool. People use it all over industry. It's created by the GPU Open folks at AMD. So this is a tool for managing memory allocation. It's very easy to allocate memory in Vulkan. It's hard to do it well. And so this tool tries to make that just easy without being too hard to use. So right here, this is what it looks like. It looks like every other VK create buffer I've ever seen, except there's just like one extra line to have a VMA allocation object, and the function slightly different. So it truly is a very easy way to simply add a nice efficient allocator to your application. And with that, I was trying to save some time, and so yes, if there's any questions, any of those tools, I'm happy to answer.
Okay.
Okay, thanks everybody for having me here. This is my name is Michael Wong. I am a distinguished engineer at CodePlay, and I'm also the SYCL chair. Now, I am going to try to present this along with my colleague Marina, who might or may not get back here in time. So the theme of my talk is going to be about taking advantage of all the MIPS in your machine, as well as building a thriving community. So minor legal disclaimer. So one thing that I've always been curious about is there one language that can take advantage of all the speed in your machine, the varieties of CPUs and accelerators out there? Now, I've been in this business for about 25 years, and I've done a lot of languages. So if you do want to program a GPU, you might want to use CUDA, OpenCL, OpenACC. You might want to use HIP, OpenGL, Vulkan, discussed here, DirectX, Intrinsics, C++ AMP, OpenMP, and yes, I did OpenMP for quite a while, and SYCL. You want to program your vector. Many machines now have vector units, and if you want to do program your vector unit, you might have, most of the time, it turns out you have to drop down to the intrinsics. But it is possible to do it with OpenCL, or God forbid, if your compiler might have auto vectorizations. And then, of course, you could do it sometimes with OpenMP and SYCL. To program the CPU, you have a lot more choices. You could use any form of the C, C++ 11, 14, 17, 20, and soon C++ 23. You can use OpenMP, you can use OpenCL, you can use TBB, Silk. Microsoft has these systems called async or then continuation. Apple had these frameworks called Grand Central Dispatch. Google have executors. There's a parallelism TS, concurrency TS. I'm the editor of the concurrency TS, and SYCL. Now, it turns out that, and I may not be totally accurate here, I may have forgotten a few. You know, there are a lot of languages out there. It turns out that most of the Khronos languages, especially the ones I've identified here, OpenCL and SYCL, are both capable of programming both the CPU and the GPU. If the GPU doesn't exist, then it will generally fall back on the CPU. Okay, so one of the things that has motivated me to think about this is, you know, what if, great what if question, what if we can democratize it so that one programming language can essentially code for all these platforms, whether they be CPUs, GPUs, AI, ML chips, or FPGA. And what if we set that to be C++? So you can already access all these C++ standard libraries. Use the latest ISO C++, for instance, and access all the MIPS that you've paid for. Now, obviously, this is a very, very biased question because I do favor C++. I've been on the C++ committee for over 25 years. I'm one of the senior directors. And, you know, I used to work in OpenMP. I was CEO of OpenMP actually for many, many years. And I've always felt that, you know, that language is fantastic for C and Fortran because it was designed in that era. But it wasn't really great if it was C++. And you know, I tried. I was trying my best to try to make it work. So stepping back from that what ifs, let's have a look at some of the things about Khronos. Now, Neil already talked about this in his summary talk before lunch. I will isolate you to focus on beyond the 3D graphics, 3D assets, and the portable XRs, the parallel computations for vision, camera, inferencing, and machine learning. And there is where you find all the languages that is involved with that, and especially SYCL. And then across the bottom, you see that newest group, the newest kid on the block is SYCL safety critical. Now, this is how Khronos standards for parallel computation relate to each other. There is an increasing interest in parallel processing acceleration to combat the end of Moore's law, as processor frequency scaling gives way to parallel programming. And we see that because there's so many more opportunity for parallelizations. Most of the convolution networks are just beautiful for these kinds of opportunities. At the lowest level, the closest to the hardware, Vulkan is used for programming GPUs. And OpenCL enables software to use any mix of available heterogeneous processors. Now, both OpenCL and Vulkan provides parallel acceleration of shaders or kernel programs compiled to Khronos SPIR-V intermediate language. SYCL and OpenVX, however, is at a higher level, in that they are frameworks for increased application portability across diverse processors. Now, SYCL enables parallel programming using standard C++, and OpenVX uses graph abstractions to express vision and inferencing functionalities. SYCL and OpenVX may be accelerated by the lower level Khronos APIs, but that's a choice left up to the implementers. If you want to go away after this is the one slide I implore you to remember. No, don't actually go away. There's actually a few more things to talk about. But this is the one slide you want to remember, that SYCL is really just a single source C++ parallel programming model. Now, I came from IBM, and at one point we used to use a cell processor on PlayStations. I don't know if you guys recall that. And that is not single source, okay? And I was one of the poor programmers who had to make it work in terms of the fact that, you know, the GPU source was in a separate file, and then you have to use DMA. It was okay for that time. But today we kind of know that the way to, and I've been doing language design, I've been a language designer for the better part of 20 years, is that the right way is to try to have it as single source as possible, because what that does is it gives you safety. When it's in a single translation unit, you can actually type check. You can't do that if they're in a separate source. Now, in some cases, that might not matter. In this case, we want specifically for it to be able to type check, so that you can now ingest major C++ libraries, which might be template libraries. Okay, that is really the straw that broke the camel's back for me in OpenMP. You cannot ingest major template libraries. Okay, you would have to write everything from scratch. And the principle of today's computer programming is that you don't redo everything. You build on what's been done before. So this explosive ability gives you the fact that now you can ingest TensorFlow, which is an all templated C++. And then from there, you can go to have a two pass, where one pass is a SYCL device compiler, and another pass could be any major CPU compilers. And honestly, I worked on almost every one of these guys, starting with the IBM Visual 8 C++, the Intel one, the LLVM one, the GCC one. And the outcome of that are these accelerated code that can be passed into device either through, at one point, just the OpenCL compiler branch. But today, the big thing is the red circle on the right, where it enables you to use it for any device, just by creating a specific backend. And it turns out it is ridiculously easy to build such a backend for almost any device. People have done it for AI devices, student devices, NEC devices that were not the mainstream major, AMD, ARM, Intel devices. That's really the real trick. And along the way, you also get the ones in the middle where, because it's C++, you get tiling, kernel tiling for free if you do it right, okay? Okay, so now you can all go back to sleep. The rest is just more of this stuff. Okay, so I did come from a high-performance computing world of supercomputers that are fighting for petascale and exascale preeminence. And I'm really happy to be here in Japan, where one of the top 500 leader, Fugaku, is actually only about 30 miles going that way in Kobe at Riken Supercomputing Center. I'm going to go see them after this. I don't think they're the #1 anymore. I think it's now back to the United States. This fight just keeps changing seats every year. Between the Chinese, the Japanese, and the Americans, trying to be the world's fastest supercomputer. So one thing I've learned from decades of experience working with parallel computing model is that there has to be longevity in the programming model. Programming models have to last 20 years because the workloads last 20, 30 years. But the hardware changes every 5 years. Often, and I don't know if this is a DOE thing, Department of Energy thing, they deliberately choose different computers every 5 years. One year it's a combination of IBM with NVIDIA, next year it's AMD with NVIDIA, another year it's Intel with NVIDIA, now it's Intel with Intel, or AMD with AMD. think they honestly do that deliberately to spread the money around. I have no proof of that, by the way, so don't quote me. But I've been doing this for 20 years, and every year they try to, honestly, they choose different computers. So this year, you'll see that the major supercomputers out there all have different CPU and GPU combinations. And what's worse is they share the computer amongst all the labs. So when you write your one code, it has to run on all these potentially different supercomputer combinations. So you can't you really don't want to rewrite the code for an AMD GPU or an Intel GPU or an NVIDIA GPU. But this is what the vendors want you to do. They want you to be locked into their thing. And Neil made a great point. The point of open standard is that it fights this kind of locked-inness. Okay. Now, I'm not complaining. I mean, everything kind of have to start out as locked-ins, but at some point it needs to open up. All right. I'm just going to jump through. SYCL 2020 was launched in February 2021. It brings a new level of expressiveness to SYCL with a lot of features that is pretty much C++ 17 aligned, like unified shared memory, parallel reductions, subgroup operations, class template argument deductions. SYCL, I think, is now, over the last 7 years that I've been involved, is now mainstream, open standard, open source. But I argue that even more important than the cross-company and collaboration, the co-design for extreme heterogeneity, great buzzword, the real treasure of SYCL, in my view, is that it has a thriving community of people who wants to keep, bringing more and more workloads like GROMACS, like LAMPPS. These are major, huge workloads to SYCL. It's very exciting. A very exciting development is that SYCL now works on Compiler Explorer. You can literally run SYCL off of a web page. In fact, if you type that particular line in Godbolt, exactly as it is, it will run this. What is this? This is a vector multiplication program. Okay. Chris Gearing from Mobileye said when I showed him this, says, "Oh, I love using Compiler Explorer. It's way more fun. It's actually more fun than work." And I agree. As a compiler developer, and I used to be a compiler developer like many of you, we would spend our days comparing Godbolt output, assembler output, to see which one is generating better code. If you were a user, you would do it all the time to see if one compiler is faulting more than another compiler. And that way it allows you to report a bug. Okay, so across the board, people are really great at using this web page compilation. Now, one caveat, Compiler Explorer from Godbolt only really work on CPU. They actually don't understand GPUs. So all this is actually just running on the CPU right now. And that's okay. And in fact, they want to work with us, Khronos, to try to provision their Amazon AWS services with GPU devices. They just don't understand. It's surprising. There's a large part of the world who don't understand anything about GPUs. I was one of those neophyte about 10 years ago before I joined OpenMP. Now, you can go even more. It turns out you can generate a bunch of IRs. And even on the third column, the triple set claims it's SPIR-V IR. Don't believe it. I can tell it's not really SPIR-V IR. I think it's a mash of LLVM IR because there's commands in there that doesn't exist in SPIR-V. But if you type that in, you'll see it, and you can get the compilation result instantly. So right now it can run, it can generate IR, but I want to do more with it. It only works right now on the Intel Clang branch, and I want it to be able to work for all three of our main compilers. All right, so just like SYCL, and because it is open, RISC-V is growing like fire. It's a free and open RISC instruction set architecture. There's no license required, but the engineering can be open or closed. And like SYCL, it is a very collaborative approach across the community. I like to think of it as the Lego block of ISA instructions. You could start with a base set of instructions of roughly 40 instructions, and then you can add optionals for vector intrinsics, for atomic support. You probably want atomic support as a minimum for OpenCL and SYCL. Okay. I'm actually chairing one of the group on data center and cloud computing, trying to get them to work on building, adding an accelerator special interest group. That will come for sure. All right. So in that vein, I've tried to marry both parts of that in my life, both as a SYCL chair and RISC-V cloud computing chair, so that we now have two major European projects, roughly 3 to 5 million, that is dealing with trying to bring SYCL to RISC-V on both data center and cloud computing. All right, so the point about SYCL is because I have a triple life, I have C++ as well. I want to make sure that SYCL follows a parallel industry initiative, so that because SYCL is so much based on ISO C++, it must follow wherever C++ is going. So C++ has been going on a every 3-year bus train model release. And I'm one of those senior directors that make sure that that happens. And I also want to make sure SYCL kind of follows that. So SYCL 2020 was released and it was based on C++ 17. Now, C++ 20 is 23. I'm heading to Varna, Bulgaria in about a month, where we're going to put out C++ 23 and make sure it gets sent to Geneva. So I'm absolutely certain C++ 23 will go out on time. And the next SYCL is also being worked on right now. Now, you would think that logically it should be based on C++ 20, but it turns out there's so many things in C++ 23 that is important that we might go jump through 20 and go to C++. One of the big things is now in C++ 23, you can actually have honest to goodness square subscript operators for array with a comma. And it doesn't, and it's not interpreted as a comma sub-expression. They have to change the language to enable that. Okay. And that what that does is it enables true array capabilities. Instead of these fake array capabilities where it has to be templated or parenthesized or something, you know what I'm talking about. Right? All right. So the major SYCL implementation are these three, and it's DPC++ from Intel, Compute CPP from my company CodePlay, and PIPSYCL from Heidelberg University. Now, this is what's funny about it. The compilers aren't built by the vendors. It turns out that the thing with SYCL is anybody can build a compiler that works for multiple vendor platforms. So we're no longer waiting around for Intel or IBM or NVIDIA to put out a compiler for it. It's totally possible to do your own independent one. The best proof of concept of that is PIPSYCL. They are just basically going off and just building it to work on AMD's, Intel GPUs. In fact, last week at SYCLCon, IWACO, Axel Alpe, who leads the compiler, just made it work on the Intel Ponte Vecchio, which is a brand new GPU that just came out. Pretty amazing, I think. And then, of course, there, like any great baseball team, there's a great farm team of compilers. And this kind of proves how easy it is to build it for pretty much anything. You know, you have SYCLCAN, which is SYCL on Vulkan backend, built by a bunch of students. You have Celerity, which is built by scientists. It's Salerno University. You have Paul Kier's, and I love this name, Motorcycle, that's built for as an educational toy that so he can teach his graduate students. There's now new contribution this year in terms of the PIM, the processor in memory from Samsung, and NeoSYCL from Tsubasa on the SX Aurora machine using the NEC CPUs and NEC VEC engines, as well as Huawei building their Baishan compiler for the Ascend AI chips with MLIR and TVM. So if you're building, there are probably some quick points to start. If you're starting from scratch, SYCL is a good place to start. Future-proof, open, easy to use, and you know you can use your ISO C++ code as is. If you're starting from C++, you can just add SYCL to existing C++ software. If you are starting from CUDA, you can port from CUDA to SYCL, and you can keep the performance on that GPU. And if you're starting from any other language, SPIR-V is standard, enables not just SYCL, but also new languages, okay? So down the bottom are all the companies that are now part of the group. Massive explosive growth, Stream HPC, Qualcomm, Mobileye, Coplay is now joined into Intel, Xilinx is joined with AMD, but Samsung is there now, Huawei's there. Have I missed anyone? And across the top, you see some of the news about some of the workloads that's being built, like GROMACS, which is a major molecular dynamics code, computational fluid dynamic codes. So we think we can handle most things, and we can handle codes that are like hundreds, thousands of lines, millions of lines long. Okay. So just I want to look at how SYCL works in different domains. And this is how all these Khronos standards could be used in a typical embedded in vision or inferencing applications. So trained networks can be encapsulated in an NNEF file, for instance, for import into the target system in two ways, either ingested into an inference engine, such as OpenVX, or passed into a machine learning compiler to generate code that executes inference operations. Now, either the compiled code or the inference engine API is linked into the applications, which may also be adding a SYCL compiler to generate additional parallel code if the application is actually written in C++. And the code is going to be generated for all these methods together with lower level application code and can target OpenCL or Vulkan lower level APIs to portably reach into hardware processors. And these are some quotes from all these embedded automotive AI safety groups that are using SYCL, like Renesas, Xilinx, NSI Techs, Imagination. You guys know, NSI Techs is actually here. You guys know Hideki Sugimoto, the NSI Techs CTO. All right, excellent. All right, so how is SYCL being used in supercomputers? This is my area. So super high performance computing and supercomputers these days is actually not just in national computing labs. They're also in automotive self-driving cars. It's essentially a supercomputer on wheel. And what they tend to do a lot of things like there are really three kinds of workload that they do. One is simulation, which needs a high performance computing language with solvers and parallel runtime. The second one is data science, which needs a high productivity language for big data. And the third thing they do is learning, training, inference, and it needs a high productivity language for ML. Now, these have been traditionally been supported by the top three languages, OpenMP, mostly for C and Fortran, a mix of CUDA, OpenACC, and OpenCL, and now for C++ specific code, they turn to SYCL. Now, and it's not just SYCL, they are also in the US National Lab, there are these things, they have developed their own frameworks called COCOS and Raja to try to help with these. And so the development workflow for science problems starts with one usually choosing an algorithm. And unlike before, today, that choice needs feedback knowledge of the system architecture and tools. And those tools need to have control of the data layout, the data movement, and the data locality, and as well as the affinity to the CPU, to the chip, or they will become non-performant. For highest performance, you need to control these aspects. Now, SYCL and other C++ framework enable these parameterization and dynamically configuring algorithms through C++ capabilities like templates and inlining. The second thing you do is you implement and test the algorithm. And the third thing you would do is optimize the algorithm. And traditionally, this was the only step that needed architectural and tool knowledge. Not anymore. Today, they really want the knowledge at the very first step, the choosing of the algorithm for the target. And that's why they're turning to C++, because that's where they need the parameterizations. It turns out that to reach exascale supercomputing, that's 10 to the 18 floating point operations per second, there are two that are now using SYCL, A&L's Argonne National Labs Aurora supercomputer, which is an Intel combination. NERSC, Lawrence Berkeley National Labs Perlmutter, which I think is an AMD NVIDIA combination. I have to check because there's so many combinations here. And then there are going to be two other ones, Frontier and El Capitan, that's coming as well too. And we're going to be in those. And under exascale computing, of course, Argonne and Chineka from Italy, the supercomputer that's there, are also interested in making sure to use this, as well as in high performance computing from Innsbruck University, Salerno, NERSC, and Intel. So SYCL enables supercomputers, and it's fantastic as a universal programming model for all device types, starting right now with the US National Lab across Europe, Asia. There are many petascale and pre-exascale supercomputers that have many different varieties of CPUs and GPUs and FPGAs, and often with interconnected usage agreements. So right now in the European Processor Initiative, HIPSYCL is being used on Leonardo, Lumi from Finland, and Carolina. I think Carolina is in Czechoslovakia, or one of the Czech Republic countries. But these are the countries that are going to be using them. So turning towards SYCL for machine learning, SYCL is a long pedigree in machine learning, and recent implementation shows its use in the RISC-V vector extension kernel compilation flow for forward convolutions. Huawei is using it in their Ascend AI chip for MLIR and TVM. And historically, Codeplay has converted to SYCL TensorFlow EigenVision CPP and implemented low-level convolution operations in SYCL BLAST, SYCL DNN, and SYCL ML. And most recently, that work has extended to 1MKL. So I envision a need in the future of a new technical study group for SYCL for machine learning, just like there's for Vulkan ML. The other thing we're turning to is automotive support. We've already have an AUTOSAR liaison group. I'm chairing that. And we're building along with AUTOSAR and a company in Ukraine called Intellius, a SYCL demonstrator that allows you to use this in a offloading hardware accelerator in an autonomous vehicle. Okay, it's very exciting. However, the thing that's going on in Ukraine is slowing it down somewhat, as you understand, because sometimes the power goes off. So we're going all in on safety critical, and that involves a lot of ISO groups, as well as United Nations. It started with this United Nations directive, WP29, that directs all of ISO to turn towards building rules that governs the safety of autonomous vehicles and then ultimately machine learning. So the one that starts that covers automotive is 26262. It's very well known. And now they've branched towards something called the safety of the intended functionality in 21448. And soon 8800 PAS is going to be talking about how to make machine learning safe. And there are a huge number of other groups like UL 4600, MISRA, SAE, and SC42 that is talking about this. So this is where I want to invite my colleague, Verena Beckham, to come on and talk about safety critical standards.
Hi, yes. My name is Verena Beckham from Codeplay. And I'm the chair of the brand new SYCL SE working group within Khronos. Khronos has over 20 years of experience creating safety critical versions of their APIs. The idea is always not to make the system safe, but to allow users to more easily make it safe. So to develop APIs or to modify existing APIs to make applications that use the API more easily to be certified according to the safety standards that are usually required for the safety critical industries. As well as allowing the applications to be certified, the API also makes it easier for the implementation of these APIs to be certified. So we've got SC versions of both OpenGL versions, and that allows you to do safety critical graphics. We've got OpenVX. OpenVX has got a safety profile. So you can do neural net and vision applications in a safe way. Then there's Vulkan SC, which was released, I think, last year, was it a year before? And that allows you to do low-level graphics as well as compute. But up to now, there's been no way of doing safe compute at a higher level. And that's where SYCL SC comes in. And we are a brand new effort that our working group was only created in March 2023 this year. But we really hope that we can open up SYCL to the safety critical industries as well. So up to now, it's already been very popular in HPC and other industries. And we now want to allow the safety critical industries to also have a part in that. And safety critical industries are all the industries where safety is really the most important factor. And that's where a failure in your system could lead to injury and even death.
It didn't work for me.
And this is how the new SYCL SC fits into the Khronos ecosystem. So we believe that SYCL SC will be used mostly or often in an AI context to implement AI. But we found that AI applications are never just AI. So they're never just neural networks to be executed. So you've got the usual frameworks that can generate neural nets, and you can export them using NNEF. But it's not just the neural nets that you want to run and then you're done, but there's a lot of glue code. So there's data processing, there's sensor fusion, there's decision making. So we think that application developers will use SYCL SC perhaps as a backend to other frameworks, but also use it manually by writing SYCL SC code. And then SYCL SC, so SYCL SC is on sort of a level with OpenVX, so they could be used together and can be accelerated under the hood by things like Vulkan SC, which is also safe, OpenCL, and any other. It could also be a custom backend. And what does SC mean for SYCL? What is it that we need to modify in SYCL to make it usable in a safe context? So there's really three topics. So one is we need to make allow the execution to be deterministic. And that means that the application needs to, every time it's run, provide the same results, but also provide the same results in the same time frame. So in safety, it's extremely important that you don't just, detect someone crossing the road, but it is no good if you detect it 5 minutes too late, then you've already gone past it. The second topic is robustness. So we want to implement, or we need to implement comprehensive error handling. And in typical application development, software development, the behavior of the program when an error occurs is usually not thought about very much. The application developers would, give up. You say, well, that's it, you crashed, restart. But in a safety context, it's really not acceptable to just crash. You have to be sure that even if you do encounter an error, that you continue on safely, and also that you report the right error with the right amount of detail. So that's something that needs to be improved on SYCL. Other examples of robustness include removing ambiguity in the API and clarifying undefined behavior. And finally, simplification. So this is all about making it easier to certify the implementation of SYCL SC, because when you implement SYCL, you have to compile it down to a library, and the library will actually run, the runtime will actually run in your safety critical context. So for example, in your car. And that means that the library also has to be certified according to these safety standards that are expected in the safety critical industries. And to make that easier, we need to simplify SYCL, because as it is, it's too large and it contains behavior that is very difficult to certify in an online system. So there'll be an effort of perhaps cutting down the API to make it more attractive to implement. So that's it. If you want to find out more, there's a link here to Khronos. or you can also email me. Thank you.
All right. Okay, we're down to the last slide. Some final words. Programming models have to last, must persist. SYCL can take advantage of all the MIPS, not the only one. I noticed that OpenCL can too. SYCL 2020 launched in February 2021. Phenomenal growth. There's a huge thriving community, which I think is our most important asset. SYCL SE is the newest work group in Khronos, and we can be part of any standard programming model for HPC, embedded AI, ML, and automotive. Last slide is talking about industry engagement and how you can work within SYCL. This is a pretty standard slide for all of Khronos. All of the frameworks all have this kind of concentric circle where you can start either inside the working group or for no cost, part of the advisory group, or work on the outside on GitHubs or on the SYCL forum. Thank you very much. Thank you very much to the Vulkan folks for allowing us to be part of you guys. Enjoy. Cheers.
Good afternoon, good evening almost. So my name is Karen Gavam and I'm the CEO and also engineering director at LunarG. I have been running the companies since shortly before the Vulkan 1.0 release. However, LunarG has been involved in Vulkan. I think their work actually started almost a year and a half before the initial release of Vulkan. But anyways, I manage all the software engineers that are doing many of the ecosystem tools that you folks are using, such as the loader, the validation layers, and the Vulkan SDK also is packaged and delivered by our organization for download on our website.
Hi, so I'm Ralph Potter. I work for Samsung, or Samsung MX in particular, so the mobile handset portion of Samsung, where I'm lead standards engineer for Khronos, which means that most of my time is spent on Vulkan, thinking about Vulkan for mobile GPUs, issues for developers on Android, and that sort of thing.
Hi, I'm Chris Glover. I'm the technical lead for Android GPU, which is responsible for graphics APIs and stuff on Android. And I'm chair of the pipeline creation TSG, which is responsible for developing improvements for GPU state management. So we were the TSG that produced the graphics pipeline libraries and some other extensions.
So you've already met me. I'm Tom Olson. I work at ARM in the media software group doing things for the Mali GPUs. But basically, I'm a standards wonk. I have been involved with Khronos for 21 years. I've been chair of, well, I was chair of OpenGLES from 2006 to 2016, and of the group that became Vulkan starting in 2012, and I'm still here. So there's practically no getting rid of me.
Okay, well, so I'll start this off with a question here, but I'm really hoping that we can get questions from the audience on any topic under the sun. And we had a bunch of great discussions today and a lot of topics that piqued my curiosity. I think I'm going to start one, since this is a developer event and we're trying to give some perspectives to the developer community. Let's start with the developer ecosystem. I'd like to ask the panelists what their kind of perception is in terms of the developer ecosystem, where we came from, where we are today, and what are the opportunities to improve in the future. And maybe start with Karen, since she's that's part of her day job.
Where we came from, oh my God. Literally, when I took over LunarG, it was about 4 months before the public launch of 1.0. And I'd been out of graphics for a while, so I was fast trying to figure out what the purpose of shader compilers were, because when I was in graphics before, it was all fixed function pipeline. The spec was going to release on a certain date. no matter what. We were scrambling like crazy to have a Vulkan loader and validation layers. It was very chaotic, very messy. It was like throwing spaghetti on the wall to see if it would stick. But we succeeded. We got a 1.0 release out. We had stuff functioning well enough that developers could start using the API. But it was really scary, chaotic time. And here it is 7.5 years later, I think. And if I just reflect on the progress that has been made, I mean, the way the state of the first most prominently used tools, the loader and the validation layers, compared to first release, you can't even compare the state that they are in today versus the first release. We've made really good progress in the overall architecture and quality and reliability and the ability to release SDKs on a known schedule with some amount of predictability, our ability to respond quickly to developer issues. And then we've been able to expand and add many more developer tools. So yeah, it was total craziness to, I feel like, a lot better predictable situation, but still lots to do. And there will always be lots to do. And what do I get excited about the future? It's really about the cross-platform nature of this API and how all these players in the industry are all collaborating together to make this cross API work, and the opportunities that exist in the future because of that collaboration.
So I guess Marty's question, like my view on the state of developer tooling, the like pithy version that's going to get quoted is could do better, but in reality, we have some things that are really, really amazing. And I have to say, the validation layers are like a standout, indispensable thing. The validation layers are amazing. The SPIR-V tooling stuff is good. There are some areas where I think we have some challenges still, like GPU debugging is hard the world over. It's particularly hard in a multi-vendor world. But I guess I have to calibrate my expectations compared to where we were with GLES. We're in a good place, but there is absolutely more that we could do. And I guess are continuing to look at and should continue to look at.
Get off my wire. Yeah. You guys kind of stole the good answers, so I have to. I guess I would say that one of the great things about having an open ecosystem is you do get some really examples of excellence in some areas. And we see that like all the stuff that LunarG is producing is excellent. RenderDoc, I think, is a shining example of something great. And kind of a story related to RenderDoc. I remember when it was new, and this actually it wasn't on Vulkan I was trying to capture, but it's related to RenderDoc. Was trying to capture the scene, and every other tool I would use would fail or take a long time and then fail. And RenderDoc just worked, and it's been like that ever since for the most part. And I think that's one of the strengths of having like this open ecosystem where people, you get many contributions from people to fix their specific problems. It's not walled off, which is very nice. But there are things that need to get fixed. Like Ralph mentioned, it is a bit chaotic and disorganized. We don't have a top-down dictator with some grand vision of how everything's supposed to be. And that means it's some effort for us to keep it organized. So that's where some of the work has to happen, I think.
So Karen and Ralph took the good answers and you took the middle, the mediocre ones. I'll give you the bad one. I mean, from my perspective, as old guy, having been in this business for a long time, there are times when I despair and I look at the quality of what we can do, or not the quality, but the level of integration, the cleanness, the polish that you have in Apple documentation and support, Microsoft documentation and support, and we can't do that. And so sometimes I despair, but on the other hand, other times I think, well, that's how it is. We are the way we are for a good reason, and that is a strength as well as a weakness. And so, as people have said, the quality of pieces of the ecosystem is amazing. It is better than anything that Microsoft has, validation, for example. And there are some other examples, but I'm blanking on them because I'm very tired. So I think for me, it's a process of giving myself a reality check every so often, saying there are things we can do and things we can't do. And they are different from the things that other players in the ecosystem can do. I think where we are now is unspeakably far ahead of where we were with OpenGLES, when the working group didn't even understand that there was anything we had to do except write the spec. Well, we did actually write conformance, which was a step forward from OpenGL, but who had nothing. But yeah, we're enormously further along. I still feel bad that we can't offer developers the level of polish that we would like to, and on the other hand, I'm enormously grateful to the people who are doing the work to get us so far along as we are. That's a rather, I am Swedish. It's a rather pessimistic view of the world. It's just how I am. Suck it up.
Okay, yeah, that was pretty good, actually. I like that. So I'm going to open it up to the floor. If anybody has questions, please step up to the mic and so we can get it recorded. We appreciate it. Any questions from the audience?
So I'm a hobbyist graphics developer, and recently I started experimenting with ext descriptor buffer. It's good, a little hard to debug at times, but I was wondering if there's any plans to do any type of code snippets for it, like how there is for things like images frame buffers on the repo for Vulkan snippets. It's really useful. One of the things I really find in particular is difficult with it, even though Hans Christian spoke about in his article, is dealing with static samplers specifically. So just curious if there's any plans to do further documentation on it, because I feel like if I wasn't actually a part of the working group, I would have never figured that API out.
You think any of this is planned?
I hope it is.
No, I have just now learned about an amazing website called Vulkan Snippets, which I had no idea existed. I mean, you're telling me there is such a website?
Yeah,
yes.
there's I found a bunch of snippets off there. There's ones for how to deal with subpasses and all of the how to do image transitions and stuff. I thought it was maintained by Khronos. Okay.
I've never heard of it, but actually this speaks exactly to what I talked about, that is that we don't provide the level of polish we'd like to, but the community does amazing things, and you just kind of feel weak in the knees with gratitude when they do something, when Sasha Willems does what he does. Things Vulkan controls, the big one in that area is the Vulkan samples. And we don't control it, but Marty and the committee together, the community together, sort of co-manage it. And at least we know what's going on there. Vulkan snippets, I have no idea. So it's awesome.
I'll send you maybe I'm mistaken it for Vulkan samples, but whoever is doing this website, if they're doing the Lord's work. Also, I would really love, I mean, 2 weeks ago would have really loved a Vulkan samples on ext descriptor buffers.
And where are we with descriptor buffers? Is that on the radar?
Yeah. Oh, yeah. In fact, I thought we had that It might still be an implementation, maybe it might not be merged, but that was one that we have been working on. So yes.
Okay, or maybe I didn't Google hard enough to find it.
Well, I mean, if you just look at the repo for the Vulkan samples repo, it should be in there. If it's not in there, then it's close. So
I didn't know about it either. Another thing I didn't know about earlier on was like when Spencer was doing his presentation and he was talking about being able to name the handles for I didn't know you could do that. And I have spent time like logging handles and then associating that with the validation error to figure out like what object this thing was. And I'm like, wouldn't it have been nice if I could do that? Oh man, you can totally do that.
So that tells me we're failing somewhere because we wrote a white paper specifically about improvements to validation layer, error messages and such things like being able to name handles to help you out. And it's posted on our website. We tried advertising it, but we need to perhaps get these things out better.
We're kind of diverging onto a different topic, but I'm going to say this anyway. So Spencer did a run through of like tools that are out there in the ecosystem. We've just talked about developer tools, and I had a negative kind of must do better message. So I spotted a tool that I didn't know about. Chris has just come up with a tool or a functionality he didn't know about. There is so much stuff out there, and frankly, none of us can keep all of it in our brains, but there is a lot of really cool stuff out there.
So we have an opportunity to consolidate, organize via the new documentation project.
I think that's a yes. Yes.
And just a quick update. I just checked, and yeah, Sasha wrote a descriptor buffer sample, and it's been merged fairly recently. So look again into the samples repo, and you should.
So one thing we're very conscious of when Spencer was new in the working group and was tearing up the track, doing all sorts of amazing things. One thing he did was create the Vulkan guide. And he's now working for LunarG, and he's not maintaining the Vulkan guide. And we're kind of desperate for somebody. If anybody in the community wants to operate the Vulkan guide.
That's the one that I found. Sounds familiar.
Well, the Vulkan guide does not have code snippets per se. I mean, it might have some, but well, I guess it does.
And it does not have scripter buffers. It's way out of date.
Right.
Something useful.
Right.
Yeah.
Anyway, just.
Can I say something to follow up from that about this? Hard to keep in your head where all these tools are when new ones arrive. How do you discover the new tools? There are too many. I have a cheat that I do. I just go to GitHub or I go to Google and do a GitHub specific search for list of awesome Vulkan tools. And you will find that there are many just independent developers on GitHub who maintain these exhaustive community list of all the awesome stuff, documentation. There's a lot of links to the LunarG SDK tools and things you've never heard of. And the community keeps them up to date. The one I just looked at right now is literally, the project name is awesome-Vulkan on GitHub. And it's a great resource.
And Lena, if you see something that you think is a great resource, let me know. But we do have a vulkan.org website that has a tools page that lists a whole bunch of those. We don't have all of them because there are a million of them, but if there's ones that are particularly useful, we definitely want to know about it and make sure that gets included.
Kind of related to that, a piece of feedback that we've had on Android is to use this stuff, we send people to GitHub and make them clone a repo and then build binary and then include it with their app or something, or with their build pipeline or something like that. And it's frustrating. I mean, that's something we as a platform need to look at and think about. No one else is really in a position to do that, but something like that could help at least curate the awesome list in some way.
Other comments, questions? Spencer.
On on behalf of the gentleman I met 2 days ago who was here. I forgot his name, but he was a university professor and he was looking into teaching Vulkan at the university level or teaching graphics. And I think it's a classic question of what would you tell people who are interested in potentially updating their, GPU 101 course at a university? Is Vulkan the right way to go, or and what do you say? Because it's the newest, hottest thing. How do you address that?
I would, yeah, we could take a straw poll. I mean, I have my view. I'm not sure it's how widely shared it is, but my view is the last thing you want to do to teach when you're trying to introduce students to the concepts of graphics. The thing is that Vulkan, it's not a graphics API. I mean, it gives you shaders. It has, there is no fixed function pipeline. If people want to learn about homogeneous matrices and how they can be used to express relations of things, if they want to learn about quaternions, if they want to learn even what rasterization is, I think it does them a disservice to expose them to Vulkan. I would say have them learn using OpenGLES, WebGL, or hopefully in the near future. I haven't seen what WGSL looks like, but if it's got graphics constructs more embedded in it, then I would say use it. I think there's a real good place for a Vulkan course at a more advanced level. So first they're going to learn graphics and, the relationship of 3D objects and surface models and scattering and all that stuff. And then they should learn GPUs, which is a different but related topic. And that's when they should learn Vulkan, because Vulkan does expose the GPU very much. That's a personal view. I don't know what other people think.
So for me, teaching graphics is actually better to have them write a software renderer, because I can write a software renderer in C++ in less code than I can set up a Vulkan swap chain. That's not even a joke. Like, it's a few hundred lines of code to write a very basic rasterizer that can load in an object and some textures and put a few lights on it. And I can't set up the Vulkan stuff in that little code. And then you teach them how to okay, now we're gonna have this accelerator and like this is how you're gonna accelerate it, and you're gonna have to manage a bunch of memory because it's async and all of this stuff, and teach all that complexity later.
So coming at this, well, first I guess I'll hit Tom's point and then I'll come at it from a slightly different angle. Like, I think it depends what your goal is when you say teach people graphics. Like, if what you want to do is teach them the fundamental maths of graphics, I mean, maybe you get them to write a software rasterizer, maybe you give them some exercises in MATLAB and just something that's got plotting tools. You can do that stuff. It's maybe not the most engaging. It's not as cool as getting like real-time graphics on the screen, but I think teaching graphics fundamentals and teaching how to drive a fast, efficient GPU pipeline are two wildly different things. So if you're talking about teaching students how to get going, then no, Vulkan probably isn't the place. But then on teaching Vulkan itself, I guess 2 plugs from Vulkanized earlier in the year. First of all, TUV have an amazing Learning Vulkan course. It's on YouTube. You can find it from the Vulkanized stuff. They also have course notes and whatever out there on YouTube. That's a great place to start. And one other observation that was made at Vulkanized earlier in the year that really hit me is that it's easier to learn Vulkan through Vulkan Compute than it is through Vulkan Graphics. Like, use Vulkan Compute to write a rasterizer if you want to, but like that stuff, because you don't deal with so many bits and pieces that are tied to the graphics pipeline, it's a more tractable starting point than like, here's our 4,000 pages of spec with all its idiosyncrasies and nasty corners.
I agree with Ralph. How about that? But let me add on that. No, really, for graphics concepts, no, not Vulkan. But if you're actually looking perhaps into GPU design or how do the what's going on underneath, then yes, start looking at Vulkan. The Vulkan specification is just specifying a GPU, in essence, is what it is. In regards to your comment about compute is an easier way to learn, I found that really interesting. This is work in progress. So we have this Vulkan SDK with all these tools in it, but we don't have an example in the SDK that shows how to use each and every one of those tools. And we're going to create a simple example that then demonstrates how to use each tool, and it's going to be compute based, because we don't want to get it too noisy with everything else that you have to set up to be able to, render some graphics.
Yeah, we have time, I think, for at least one or two more questions. Others from the audience? I can go on for hours with questions, but preferred. Yep. Yeah.
So pretend I'm not a part of this group, right? Part of Vulkan bring up is that there's a lot of extension loading and then turning on features, etc. Are there plans to? I've heard in the past there's been some talk of tiers, but are there plans to simplify that? Because chaining like 30 structs together is really fun, only in some ways, but most of the time really not. And also related to that is the properties. Is there some kind of will there be some kind of grouping system for, let's say if I want to turn on ray tracing and all the associated extensions and properties? Is there, short of just me having to look through all the documentation, is there going to be a more focused way to deal with that in the future, like an easier way?
One word, profiles. I mean, I hope that's the answer. If it's not, I really want to know why not. But yeah, a major part of the profiles tool that LunarG created, the profiles header library, is to say, here is a profile. Does the implementation support it? Yes. Okay. Please create me a context with everything enabled, or let me selectively turn off a few things. If it does that, it was going to at one point. Okay. And now nobody has gone through and defined a ray tracing profile, but you could. Of course, it's all open source, and the profile builder and the library header builder are all accessible. So you could write your own profile, teach the generate a header library that knows about that profile, and then you would just include that.
Does it allow you to have separate profiles to control different feature blocks?
I'm not quite sure. I'd have to think about what that means. Christoph has talked about things that would do like logical operations on profiles so that you could take the union and difference and things like that. I don't think that any of that is supported, but he's thought it through at least. No, he has?
I'm going to get myself in trouble because I don't understand enough details of usage, but there is a tool that he has created where you can intersect or take the union of various profiles and combine them and create such a new profile. So yes, he talked about it and he did it.
So yeah, the answer to Hai's original question, yeah, I think the correct answer is profiles. But while Hai was talking, it brought to mind something else that I recently stumbled upon that I should have known about a long time ago. You know, I've been involved with Vulkan one way or another since like the start. And why was it that 3 months ago I discovered that Charles Geeson's VK Bootstrap thing exists? Like that thing is amazing for like spinning up a Vulkan app, doing all the the thousands of lines of boilerplate code you need is by including one header and one C++. Why did nobody tell me about this thing? It's a utility library to drop into your application that will do all the boilerplate. Like maybe you don't want to use it in your production app, but for your quick, like I want to try an experiment, give me a physical device and a logical device in an instance with a set of extensions. It's amazing.
This thing is so amazing that I just need to put an explicit plug so people know where to find it. Whoever's listening online, go to GitHub, search for VK-Bootstrap.
And Charles does it on his spare time, free and copious spare time that he has, and evidently is quite humble. Hearing all these kudos about it here, perhaps I should have been taking it and putting it in the SDK.
I'm definitely going to put it on the
Maybe
website.
because he saved me so much time in the last few weeks.
Yeah, we'll get that added to vulkan.org so you can find a quick link to it. Other questions? I have one more. It's quite a bit different topic, but Michael did a fantastic job on the SYCL talk, and I saw Vulkan as a target on several of his slides. I was just curious about impressions from the panelists here about the future of compute with Vulkan, and I know it's primarily for games and for graphics, but is there a role for it in compute beyond that, or and what's kind of the future of compute with Vulkan in just a perspective from folks on the panel?
I think there's a role for it. It's not quite got everything compute-wise that OpenCL has. There are particularly some compiler SPIR-V things that we need to sort out that we are actively working on sorting out. But at the same time, I mean, I'll say that we at Samsung have a project that is dependent on being able to do everything that OpenCL can do in Vulkan. So I expect us to get there. And yeah, there's loads of really cool compute stuff out there, and there's no reason why you can't run it on Vulkan. But yeah, there are a few specific gaps that need filling. And as far as I'm aware, well, everyone that I'm aware of is being worked on.
That's great.
I have a feeling I'm going to steal Tom's answer. So I view graphics and compute as not separate, and I know a lot of people do. They think Vulkan is a graphics API, but it's really, in my view, it's a way to program accelerator devices, and you can see that we have extensions for video and stuff like that. Like if there's a piece of hardware on the device and it's an accelerator and it's asynchronous, and you can communicate with it through command buffers, then Vulkan's a great API for that in general. And we're seeing more and more graphics pipelines use more and more compute. So really they're intertwined. So yeah, but Vulkan is an asynchronous accelerator programming API.
Actually, that wasn't my answer. It's a good one. I like it. I agree with it. But yeah, I mean, what I was thinking, and I will say that I know OpenCL reasonably well. SYCL is a bit of a closed book to me, except that I know that it's single source. So I don't understand entirely what I'm talking about. But I'm a former college professor, so that doesn't matter. I can talk about it anyway. From my point of view, if you think of, I talked about Vulkan as a HAL. I just think that my guess is that SYCL is at such a different level. And Vulkan is absolutely going to have a role where it is sitting under any, or it could have a role where it sits under any SYCL implementation that has a GPU component. Because SYCL is about what? Heterogeneous computing. And it's going to want to run some stuff on the CPU and some stuff on the GPU. And it may run on the GPU through, any number of APIs. But it's not unlikely that Vulkan will be way down there in the basement, making things work. And you may not even be aware of it. That's kind of how I see the relationship between the two. Although I really do like the idea, and I really do want to see a future where directly in Vulkan I can do, well, I love CLSPV. It's my favorite concept ever, being able to run OpenCLC shaders, and dispatch them through Vulkan, I think is, absolutely something I want to be able to do.
Okay, well, we've actually run way over time. I'm happy to extend longer if there are other questions from the audience. Otherwise, we can conclude here. Anyone else have a question they'd like to ask? If not, thank you very much for the panel members, and thank you for the audience for staying late for us, and always appreciate getting that time with the development community. So thanks, we'll conclude here.